Hi everyone, welcome to GoClasses. In this session, we will continue our propositional logic discussion. So we are discussing complete propositional logic summary, and this is part 2 and this is final part. The part 1 you can find the link in the description. Check it out. Okay. So let's continue propositional logic discussion. Okay. Now we will discuss a method called by case method to solve questions quickly. Okay, if you want to solve questions of propositional logic very quickly, then you can use this method by case method. Okay, so far which method we have seen to solve questions? We have seen truth table method, yes or no? So far we are using truth table, but this truth table, this is a boring and this is inefficient and this is time consuming method. This is boring, time consuming, inefficient. So don't use this truth table. From now onwards, we are not going to use the truth table method because this is inefficient. Okay. So we are going to use by case method. This by case, this method we are going to use. And this method is actually efficient and this is analytical also. Okay. Whenever something is analytical, then that method is mostly that method is very good method. Okay, so this is an analytical method. After some time we will see another method, that is simplification method. That simplification method is also a good method to solve the questions. Okay, so right now we will discuss by case method, because truth table method, that is time consuming and that is inefficient, that is boring method, so we are not going to use it. Now let's see what is this by case method to solve questions quickly. Okay, what is this method? So let's understand. Look at this truth table. In this truth table you can see this is our propositional logic formula. Okay, this is our compound proposition and this has two atomic propositions. There are two propositional variable p comma q. Okay, so in this truth table what we will do, we will create the truth table and we will write all the truth value combinations of p comma q, because these are the propositional variable. So we will write all the truth value combinations of p comma q. Okay, so there will be total 4 combinations, yes or no? But notice one thing. Can I say that in the first two combinations, can I say p value is false? Notice here that can I say that in these two combinations, in these two truth value combinations of p comma q, can I say that here p value is false? And did you notice that here p value is true? So can I say that basically I can say that only two cases are possible, either p will be true or p will be false, yes or no? So can I say that only two cases are possible, only two cases possible? One is when p is true and another is when p is false. Do you agree with me? Only two cases are possible, when p is true or p is false. Because remember, what is p? P is a propositional variable, and you already know that whenever you have a propositional variable, then that is either true or false. If you take any propositional variable like p, then it can be either true or it can be false. Is there any other possibility? Is there any other possibility? No. This propositional variable, this will be either true or this will be false. Means this propositional variable, it will take one of these two values. Okay, one of these two values it will take. Similarly, whatever propositional variable you take, for example q, that is also either true or it is a false. Okay, yes or no? So remember, any propositional variable, it will be either true or false. Okay, so if we consider p true, p false, if we consider these two cases, then we are covering each and every possibility. Similarly, if we consider q true, q false, these two cases if we consider, then we are covering all the possibilities. Okay, I hope this point is clear. So remember, you can take any propositional variable, you can take p or q, but whenever you take a propositional variable, then consider both the possibilities, q true, q false, because when you consider both the possibilities, then you are considering all the possibilities. Okay, you can see here, when I consider p true, p false, okay, p true, p false, when I consider these two cases, then basically I am covering all the possibilities. Okay, when I consider p equal to false, then these two possibilities I am covering. When I consider p equal to true, then these two possibilities I am covering. So in these two cases, I am covering all the possibilities. Is this point clear? Let me know. Let me know. Similarly, here also you can see the same thing. Okay, here we have three propositional variable p, q, r. Okay, because you can see this is a compound proposition, or I can say this is your well-formed formula, or I can say this is your propositional expression. So in this propositional expression, there are three atomic propositions, or I can say there are three propositional variable p, q, r. So in the truth table, what we will do, we will write all the truth value combinations of p, q, r. So because we have three propositional variables, so there will be total 8 rows, or I can say there will be total 8 truth value combinations of PQR. But notice one thing. Can I say in the first 4 combinations, in the first 4 truth value combinations of PQR, can you notice P value is true? Can I say that in the first 4 combinations, can I say that here P value is true? Okay. Similarly, you can notice that here P value is false. So what I can say that these two cases, P true, P false, these two cases are covering all the possibilities. Okay, yes or no? When I say P true, then I'm covering all these cases. And when I say P false, then I'm covering all these cases. So remember, if I take these two cases, then I'm covering all the possibilities. Okay, I hope this point is clear. Very simple. Okay, the same thing you can do for Q also. The same thing you can do for R also. So take any one variable. Okay, and for that variable, you consider two cases. That variable is true, that variable is false, because these two cases, they will cover all the possibilities. This is your by case method. Okay, this is our by case method to solve questions quickly. Now let's do a lot of practice. Let's solve this question on your screen. In propositional logic, a contradiction is a compound proposition that is always false, no matter what truth values of proposition variable that occur in it. Okay, so show by the means of truth table means, okay, by the help of truth table, show that this is contradiction. Tell me one thing, will you create truth table? Don't create truth table, that is boring method. Yes or no? So never create truth table, that is a boring method. So I can say that this truth table, okay, what you will say, you will say that this is boring method, so don't apply this. What you do, you just apply the by case method. Okay, so don't apply, don't apply truth table. Okay, don't apply. Let's solve this question by the help of by case method. Okay, so our expression, please understand our expression, let's call it h. This expression is P and negation of Q or P. Okay, it is Q or P negation. So this is our expression. Now let's solve it, and we want to prove that this is contradiction. Tell me what is the definition of contradiction. Let me know. Contradiction means always false, means in every case it must be false. Do you agree with me? If you want to show that something is contradiction, contradiction simply means always false. Okay, yes or no? Always false means in every case it is false. In every case it should be false. It should be false. Correct? Okay, so now I will create two cases. Remember, in the by case method, I am going to create two cases. What are those two cases? Tell me. Only two cases are possible, because remember, this P, this is a propositional variable. Okay, and remember, any propositional variable, it will take only one of the two values, that is true comma false. So only two cases are possible, remember. Okay, what are these two cases? One case is, the first case is when P is true. This case is possible. Another case is possible when P is false. Only two cases are possible. No other case is possible. Either P will be true or P will be false. There is no other possibility. Okay. Now you tell me, when P is true, then what will be truth value of H? What will be this expression H when P is true? So you can see when P is true, you can see that what is Q or true? Tell me, what is Q or true? Anything or true, that will be true. Yes or no? Anything or true, that will be true. So Q or true, that will be true. Now you can see. So when I take P equal to true, when I take this true, then P or this P or Q, this will become true. Okay, and what is the negation of true? What is the negation of true? You can see, what is the negation of true? Negation of true will be false. So this will be false. Now tell me, what is P and false? What is P and false? Remember, P is true. What is P and false? P is true. So tell me, what is true and false? That is false. So finally, what we got? We got false. So H is false in this case. Yes or no? In this case, H is false. Now let's see in this case what will happen. In this case, when P is false, now you can notice when P is false, then false and anything, that will be what? That will be false. Yes or no? False and anything. Whatever I write here, anything alpha, that will be what? That will be false. Okay, you can see the truth table of and. Okay, you can see the truth table of and. Check the truth table of and. False and anything, that will be false. Okay, so finally I can say that in this case, when P is false, in this case also H is false. So tell me one thing, only two cases are possible. Either P is true, P is false. In both the cases, can you notice H is false? So can I say H is always false? Let me know. In this case also H is false. In this case also H is false. So in every case H is false. So H is always false. So I can say H is contradiction. Okay, that's it. This is the proof. So very simple. So I can say H is contradiction. Okay, yes or no? So very simple. Is this clear? Now, let me tell you that you can take variable q also. Okay, you can take any variable, you can pick any variable and you can solve the question. This question you can solve by picking any variable. For example, if you don't want to pick variable p, you can pick variable q. Remember, we want to cover all the cases. And tell me, if I pick variable q, tell me how many cases are possible. Only two cases are possible. Only two cases are possible. Remember, one case will be when q is false, another case will be when q is true. Okay, because remember, q is a propositional variable. So only two cases are possible. Either q will be false or q will be true. Is there any other possibility? Tell me. Is there any other possibility? No. Okay, either this or this. There is no other possibility. These two possibility, they are covering all the possibilities. These two cases, they are covering all the possibilities. You can solve the question now also. Okay, let's solve it. So when you take q equal to false, in this case, what will be the value of h? In this case, what is going to be the value of h? You can see if I take q false, false or p, what that will be? False or p, because I am taking q equal to false. So if I take q equal to false, false or p, that will be same as p. That will be same as p. Okay, yes or no? So finally what I got p and p bar. I got p and p bar. This is what I got, h equal to p and p bar. P and p bar, that is always false. P and p bar, that is false. So can you notice that in this case when q is false, in this case h is false. And what about this case when q is true? In this case, what will be the truth value of h? When q is true, if I take it true. Now remember, true or p. What is true or p? True or p, that will be true. That is always true. Yes or no? True or anything, that is true. Okay, now we got p and true bar, because remember, when I put q equal to true, then true or p, that will be true. Now I got p and true bar. What is true bar? Negation of true is false, so I got p and false. What is p and false? That is false. Correct. Okay. So finally, what I got in this case also, I got false. Did you notice that only two cases are possible, and in both the cases h is false? So can I say h is always false? Only two cases are possible. Remember, either q will be false or q will be true. There is no other possibility. Okay. In both the cases h is false, so I can say h is always false. So I can say that h is always false. Okay. And because h is always false, that is same as contradiction. So h is contradiction. Is this clear? This by-case method, did you understand the by-case method? The logic behind by-case method, did you understand? And this is a beautiful method, let me tell you. You never have to apply the truth table. Okay, let's solve a lot of questions. Let's solve this question. Build a truth table. By creating a truth table, verify that this proposition is a contradiction. Will you create truth table? Will you create truth table? No, truth table is a boring method. We will never do that. Okay, what we are going to do? We are going to use the by case method. So tell me, in this by case method, remember, I can take any variable and I can create two cases. Okay, so again, let me use the by case method. So only two cases are possible. Yes or no? What is case one? Case one is p true. Okay, what is case two? Case two is p false, because only two cases are possible. Either p will be true or p will be false. There is no other possibility. Only these two possibilities are there. Either p will be true or p will be false. Now you can see that in both the possibilities, in both the cases, let me call this expression, let me call it h. Okay, now you tell me, in this case, what will be the truth value of h? Let me know what will be h when p is true. Okay, just put p is true. Now in this case, let's see, because your expression is what? Our expression h, that is p biconditional q and p bar and q. Okay, so this is our expression, right? Now you can notice, if I put, tell me, if I put p equal to true, if I put p equal to true, then what will be this? True. True negation will be false. Yes or no? True negation will be false. You know that true negation, that will be false. Okay. So tell me, what will be false and Q? What will be false and anything? False and anything, that will be false. So can I say this will be false? Now can I say false and anything? Okay. Yes or no? Can I say that false and anything? This is false and here. So what is false and anything? That is also false. Correct? False and anything, that is false. So finally what I got, when P is true, then this expression H is false. Now you tell me, when P is false, then what will be this expression H? When P is false, now you tell me, I am putting P false. So what is false bar? Negation of false, that is true. So this will be true. Okay, I am putting P equal to false. So tell me what I will get here. Now you can see that here I will get P false by implication Q. First, you tell me what is false by implication Q. First, let's see what this will be. What this will be. Okay. See, very interesting method I'm telling you. This is fixed, right? This false is fixed. Do you agree? This false is fixed. False is fixed, right? Okay. So now you tell me, because this false is fixed, I want to know what is false by implication Q. What should I write here? What should I write here? See, the method is very simple. You tell me one thing. This Q, this is not fixed. Okay, remember, if Q is true, then what this box will contain? If Q is true, then what this box will contain? What I will write in this box? If Q is true, if Q is true. So if Q is true, then false biconditional true, that is false. Okay, in the box I will write false. If Q is false, if Q is false, now tell me, if Q is false, if Q is false, then false biconditional false, that will be true. Yes or no? So did you notice one thing, that whatever is the value of Q, I am getting the opposite. See, already this F is fixed, because this is fixed, that is false. Yes or no? This is false. But did you notice, when Q is true, in this box I am putting false. When Q is false, in this box I am putting true. So in this box I am putting Q bar. Do you agree? In this box I will finally put Q bar. Okay, very simple. Okay, so that's it. So I can say that if P is false, then here what will happen? This will become Q bar. Okay, this will become Q bar. And you can see here what is true and Q. Okay, what is true and Q? That will be Q. True and Q, that will be Q. Q and Q bar, that will be false. Okay, very simple. So finally I can say that when P is false, then also this H is a false. Okay, so can I say H is always false? Only two cases are possible, and in both the cases H is false. So I can say that H is always false. And because H is always false, so H is contradiction. I can say that H is a contradiction. Okay, very simple. Now let's move on. Now let's solve this question. So this we have already done. Now, these questions can I give you as a homework? Let me know. The following are tautology. Can you prove it? Let me prove any one of them. Let me prove the first one. Okay, let me prove the first one. That first one, that is tautology. Okay, so let me use the by case method. Again, I will use the by case method. The remaining you can take as homework. Okay, you have to prove, remember, you have to prove that they are tautology using the by case method, or you can use any other method. Okay, but this question you can take as homework. Now let me solve this question for option A. Okay, so we need to prove that this is tautology. Now what we can do, tell me. Again, only two cases are possible. Yes or no? Only two cases are possible. So either P will be true or P will be false. Only two cases are possible. So let me take two cases. Case 1, that is P true. And what is case 2? Case 2, that is P false. Only two cases are possible. There is no other possibility. Okay. Now tell me, when P is false, then what will be this expression? Let me call it H. Okay. This expression, I am again calling it H. So when P is true, then what will be the truth value of H? Just put P true. In this expression, you put P true. So you can easily see this expression is like this: P and Q bar, P and Q bar, biconditional, biconditional, P bar or Q bar. correct? Okay, so this is the expression. Now what you do when P is true, okay, just put P true. So when P I put it true, then what is true and Q? True and Q, that is Q. Okay, so this will become Q bar. Okay, I will get Q bar. Biconditional. When I put P true, then this will become false. Okay, what is false or Q bar? What is false or Q bar? Remember, false or alpha, that will depend only on alpha. Okay, false or alpha, that will be same as alpha. Okay, yes or no? So finally I can say that false or Q bar, that will be Q bar. So I can say Q bar. Now you tell me, did you notice these are same? So biconditional will be true, yes or no? You know that biconditional, when biconditional is true, you know that biconditional alpha, biconditional beta, you know that this is true when this is true. This is true when alpha and beta are same. Now you can see here, this is Q bar, this is Q bar, they are same. They are same. Because they are same, so this biconditional will become true. Okay, because this is also Q bar, this is also Q bar. So finally I can say that in this case, when P is true, then in this case this H is true. Okay, and what about this case when P is false? Now you tell me, when P is false, let's put P equal to false. So you can see false and anything, that will be false. Okay, yes or no? False and anything, you know that false and anything, that will be false. You can check the truth table of and. Okay, just check the truth table of and operation. You can see false and anything, that is always false. So if I put P equal to false, then this will become false. So it will be like false negation by conditional. Okay, here also this P bar, this will become true. Okay, you can see true or anything, that will be true. Okay, so I can say that this will become true. So you can see false bar, that is true. So true biconditional true, what is that? True biconditional true, that is true. Yes or no? True biconditional true, that is a true. So finally I can say in this case also H is true. Okay, so can you notice only two cases are possible? In both the cases H is true. So can I say H is tautology? Let me know. Only two cases are possible. Either P can be true or P can be false. There is no other possibility. These are all the cases. In all the cases H is true. So because H is always true, this is the definition of tautology. Because H is always true, so I can say that H is tautology, or you can say H is a valid, or you can say H is valid, because tautology is same as valid. Valid and tautology, they are same. Okay, yes or no? Can I say H is contingency? Can I say H is contingency? No, H is not contingency, because remember, contingency means neither tautology nor contradiction. Okay, contingency means neither tautology nor contradiction. But you can see here H is tautology. Tautology is same as valid, so H is valid. Okay, let's move on now. This question can I give you as a homework? You need to find out these expressions, they are tautology or contradiction or contingency. Okay, these expressions, which of them is tautology, which of them is contradiction, which of them is neither. Neither means contingency. So you need to find out. Okay, can I give you this question as a homework? Okay, so please put a comment. Please put a comment. What is option A? What is option B? What is option C? Is it tautology, contradiction, contingency? Is it tautology, contradiction, contingency? Okay, so solve this question with the help of by case method. Let me tell you one thing, you practice all the methods, because in different questions different method will be useful. Okay, for a different question I can say different methods, they will save you a lot of time. We will see simplification method. Okay, so remember, for these three questions you try the by case method. We will, there is a simplification method, that also we will see. Okay, but remember, whenever you have a question, then for different questions different method is useful. So you should understand everything. Okay, understand all the concepts, and then you can decide which concept to apply. Now let's solve this question. Which of the following compound propositions are satisfiable? Do you know the definition of satisfiable? The definition of satisfiable, yes, satisfiable means at least one time true. At least one time true. Okay, means is there any case where it is true? Means can you make it true? At least one time true. Satisfiable means can you make it true? Is there a way to make it true? So you know satisfiable. So this question also I am giving you as a homework, but I will solve one option here. Okay, tell me which option to solve. Let me know. First of all, let me tell you the definition of satisfiable. The definition of satisfiable is we can somehow make it false. Okay, means it is possible to make it false. Satisfiable means it is possible to, sorry, it is possible to make it true. It is possible to make it true. Make it true. It is possible to make it true. Yes or no? So satisfiable means it is possible. There is a possibility that you can make it true. Satisfiable means at least one time true. Okay, I can say satisfiable means at least one time true. In at least one case, it is true. At least one time true. Okay, in at least one case, it is true. So, very simple. This is the definition of satisfiable. Satisfiable means it is possible to make it true. You can satisfy this. Okay, so let's solve option C. Let me solve it. And the remaining options you can try. So, let me take option C and let me check is it satisfiable or not. Option C is P or Q, P or Q, and P bar R, P bar R, and R or Q. This is option C. Okay. Satisfiable, remember that is same as tautology or contingency. Satisfiable means at least one time true. Okay, it can be tautology also. Satisfiable is same as either it will be contingency or it will be tautology. Okay, remember satisfiable is either it is tautology or it is a contingency. Means satisfiable means not contradiction. Satisfiable is same as not contradiction. Satisfiable, that is same as not contradiction, non contradiction. Okay, very simple point. Satisfiable means not a contradiction. Satisfiable means you can make it true. There is at least one case where it is true. Okay, this is the definition of satisfiable. Satisfiable means not a contradiction, or I can say satisfiable means tautology or contingency. Okay, so let's see this option C. This is our option C. You can notice P or Q and P bar R. Okay, yes or no? Because do you remember I told you, if you remember, I told you that this A and B, that is same as AB. You can write like this. If you remember, I told you A or B, you can write like this, A or B. Okay, so these things we have already seen. Now the same thing you can see. This is our expression C. Again, I will apply the by case method. Only two cases are possible. Here you have three variables. You can take any variable of your choice. So let me take variable P. Okay, again, only two cases are possible. Case 1, that is P true, and case 2, that is P false. There is no other possibility because P is a propositional variable. So either it will be true or it will be false. There is no other possibility. So tell me, when P is true, then what will be this expression? Again, let me call this entire expression, let me call it H. So tell me, when P is true, what will be this expression H? When P is true, then this expression will become true. Yes or no? This will become false. Remember, when P is true, if you put P true, then this P bar will become false. Okay, this entire thing will become false. False and anything that is false. Yes or no? So I can say when P is true, then H will be false. Okay, because when P is true, if I put P true, then this will become false. And there is and here. Yes or no? False and anything is false. False and anything is false. False and anything is false. So very simple point. So finally I can say that when P true, then H is false. Okay, yes or no? Can I stop and can I say that this H is not satisfiable? Here can I stop? Can I stop here? And can I say that H is not satisfiable? No, I cannot stop. Maybe in this case, this H I can satisfy. Okay, yes or no? Because remember, satisfiable means there is a possibility to make it true. There is a possibility to satisfy this. Yes or no? At least in at least one case, I can satisfy this. I can make it true. Yes or no? So remember, here I cannot stop. Maybe in this case, I can satisfy this H. Okay, so let me see. If I put P equal to false, then what will happen? Let me put P equal to false. Then tell me what will be H. Because I'm putting P equal to false, so false or Q, that will be Q. Okay, yes or no? I'm putting P equal to false, so this will be true. True and R, that will be R. Okay, and here it will be R plus Q. Now you can stop. See, did you notice? This I can definitely satisfy. Yes or no? See, can you make it true? Just tell me, can you make it true? this QR R plus Q. Yes, I can make it true. Just put QR equal to true, true. Yes or no? Did you notice that if I put Q equal to true, if I put Q equal to true, R equal to true, did you notice that this H will become true? Yes or no? Okay, so can I say, and here in this case, remember P is false. Okay, P is already false. In this case, already P is false. So B, because P is false. So did you notice that in this case, H is true. So can I say H is satisfiable? Yes or no? See, I can satisfy H. You can notice, I can satisfy H. You can see, I can satisfy H. I can say, I can put Q true, R true, already P is false. Okay, then you can see H will become true. So I can satisfy H. Because I can make H true, it is possible to make H true. Yes or no? Agree with me? This is possible to make H true. So because it is possible to make H true, so H is satisfiable. Okay, is this clear? So in this question, I can say that this definitely this is satisfiable. Option C, that is satisfiable. The remaining options you have to check. Okay, in the remaining options, are they satisfiable or not? That you have to check. But option C, that is satisfiable. Is this clear? Let me know. Now let's see logical equivalence. This is the next topic. What logical equivalence means? This is the definition of logical equivalence. If I give you two compound propositions, means if I give you two logical expressions, two propositional formula, if I give you, then when can I say they are equivalent? The name itself is telling you. The name is telling you equivalence, means they are always equal, means their truth value is always same. You can see if you have two compound proposition which have same truth value always, same truth value in all the cases, then they are logically equivalent. Is this clear? Means they have same truth table, or I can say they have same truth value in all cases, then they will be called logically equivalent. Okay, and what is the symbol? And what is the symbol? The symbol is like this. This is the symbol. Remember, the symbol is this. So when can I say that G comma H, when can I say they are equivalent? So very simple point. If you have propositional expression, if your propositional expressions G comma H are equivalent, when can I say they are equivalent? They are equivalent if they always have same truth value in all the cases. Okay, they are equivalent. They are equivalent. So we denote it like this. G is equivalent to H. Okay, this is the symbol for equivalence. So remember, they will be equivalent if okay, if G comma H have same truth value in all cases, have same truth value, they have same truth table. I can simply say that they have same truth table, or I can say they have same truth value in all the cases, or I can say that they have same truth table. Okay, is this clear? Very simple. For example, you can see here you have two expressions, that is, one is P implies Q, P implies Q. You can notice this expression, let me call it G, and you can notice this expression negation Q implies negation P. They have same truth table. So I can say that this expression and this expression, these two expressions are equivalent. Okay, you can notice they have the same truth table. You can see this is the truth table of P implies Q. Correct. Okay, and this is the truth table of negation Q implies negation P. Did you notice they are same truth table? TFTT, TFTT. So can I say that in all the cases they have same truth value? In this case, they have same truth value. In this case, they have same truth value. In all the cases, they have same truth value. This is the definition of equivalence. Very simple definition. Two propositions are equivalent if they have same truth value in all cases. In every case, they have same truth value. Means they have same truth table. This is the definition. So did you notice that these two, they are equivalent? Yes or no? They look different. Do you agree with me? They are looking different, but they are actually equivalent. Okay, their truth value will always be same. Okay, whenever this is true, this will be true. Whenever this is false, this will be false. Whenever this is false, this will be false. And whenever this is true, this will be true. So their truth value will always be same. You can see here again, this expression and this expression, they are also equivalent. They are equivalent because you can see their truth table is same. Okay, you can see this P biconditional Q, this expression is same as this expression. P implies Q and Q implies P. In the last lecture also we have seen this. Yes or no? These two, they are equivalent because they always have same truth table. Or I can say they always have same truth value. Whatever case you take, in this case also they have same truth value FF. In this case also, they have same truth value. Okay, so in all the cases they always have same truth value, so they are logically equivalent. Okay, very simple. Now you tell me one thing, if two expressions are logically equivalent, then what can you say about their biconditional? Okay, see, very simple note. Just understand that if G comma H are equivalent, if G is equivalent to H, okay, then what can you say about G biconditional H? If this expression, if they are equivalent, means they have same truth table, then what can you say about this expression G biconditional H? Then what this expression will be? This is very easy to find out. Okay, so you can see, remember, G is a propositional formula, H is a propositional formula. Okay, so they have some propositional variable. Do you agree with me? They have some propositional variable. G is a propositional formula. Okay, we don't know. See, G is a formula. This can be any formula. H is also any formula. Okay, so they have some propositional variables. Do you agree? Okay, so in the truth table, what will happen? In the truth table, you can see they have some proposition variable. I don't know, P1, P2, something. I don't know. Yes or no? I don't know, but they are propositional formula. G comma S, they are expression. This is expression, this is expression. So they have some variables, PQR or PQ or something. Okay, so I don't care. But you can notice, if they are equivalent, then tell me their truth table will be same or not. They are equivalent. They are equivalent. So it means when it is false, it is also false. Yes or no? When it is true, it is also true. When this is true, this is also true. When this is false, this is also false. When this is true, this is also true, and so on. Okay, yes or no, and so on, and so on. Agree? Correct? Because they are equivalent, so their truth table will always be same, or I can say they will always have same truth value. Okay, whenever this is false, this will be false. Whenever this is true, this will be true. So very simple. Now you tell me, what will be their biconditional? What will be their biconditional? If I put this biconditional, what will be truth table of this expression? I am creating a new expression with the help of biconditional. G is something, H is something. I have created a new expression with help of biconditional. What is the truth table of biconditional? Very simple. You can see F biconditional F, that will be true. Okay, true biconditional true, that is true. True biconditional true, that is true. False biconditional false, that is true. Okay, true biconditional true, that is true, and so on. So did you notice that this is tautology? Yes or no? This is always true, so this is tautology. So this is the result, that if G comma H are equivalent, then their biconditional will be tautology. Their biconditional will be tautology. Is this understood? This is the definition. This is another definition of equivalence. So remember, G is equivalent to H if and only if their biconditional is a tautology. Okay, so very simple point. If you have two compound propositions, or I can say if you have two propositional expressions, G comma H, then remember, this is another definition of equivalence. They can ask you this in the true false statement. Okay, this is the definition, that G is equivalent to H if and only if, when can I say G is equivalent to H? G is equivalent to H if and only if their biconditional, is a tautology. Okay, is this clear? Let me know. Very simple. Yes or no? So very simple point. G is equivalent to H if and only if their biconditional is a tautology. If you do their biconditional, that will be tautology. So very simple. This is another definition of equivalence. So how many definitions of equivalence we have seen? We have seen many definitions. See, I can say they are equivalent. G is equivalent to H if they have same truth table. That is one definition. Another definition, they are equivalent if they always have same truth value. In all the cases, they have same truth value. That is another definition. And this is another definition. G is equivalent to H if and only if their biconditional is a tautology. Okay, if you create their biconditional, that will be tautology. Okay, and you can see this is the proof on your screen. So very simple. So you can see this is the definition. If you have two propositions R comma S, they are logically equivalent if their biconditional is a tautology. If R biconditional S, that is a tautology, then they are logically equivalent. Okay, and remember, either you can use this symbol R biconditional S, or you can use this symbol also. Some people use this symbol also, that is also fine, because you can notice their biconditional will be tautology. So some people use this symbol, some people use this symbol, both are fine. Okay, now let's move on. So we have seen these two definitions. You can see for logical equivalence, these two definitions we have seen. Compound propositions that have same truth value in all the cases, they are logically equivalent. This definition we have seen. Also, we have seen this definition that if you have two compound proposition, they are logically equivalent if their biconditional is a tautology. And this is how we denote. Okay, denoted by V is equivalent to W. It means they always have same truth value. Okay, let's move on now. So you can see all these statements are same. All these statements, they are definitions of equivalence, logical equivalence. What is the definition of logical equivalence? All of them, remember, all these statements are the definition of logical equivalence. V is equivalent to W if their biconditional is a tautology, or I can say their truth value is always true. Yes or no? Their biconditional truth value is always true. I can say biconditional is a tautology, or I can say V comma W always have same truth value. Okay, very simple. Now let's move on. You can see in this table, again you can see this expression, this expression. Are they equivalent? Do they have same truth table? Tell me, this expression, this expression. Let's call it G, let's call it H. Are they equivalent? You can see this is our expression G, this is our expression H. Yes, they are equivalent because their truth table is the same. Okay, so they are equivalent. Okay, did you notice one thing, that let's call it G. Okay, see, let's call it G, and let's call it H. Let's call it H. Now tell me, what is their biconditional? If I create G biconditional H, what will I get? You can see F biconditional F, that will be true. True biconditional true, that will be true. You know that biconditional is true when both are same. Yes or no? When both are same, then biconditional will be true. Correct? Okay, so the same thing you can see here. When both are same, then biconditional will be true. When both are same, biconditional will be true. So can I say that this biconditional is a tautology? This biconditional is a tautology. So I can say that G is equivalent to H. Very simple. Okay. Now, tell me the answer for this question. How many rows are there in the truth table of a compound proposition made up of n atomic propositions? I told you what is atomic proposition. That is propositional variable. Means you have total n propositional variable. If you have total n propositional variables, then how many rows will be there in the truth table? The answer will be 2 power n. Answer will be option D, and this is very easy to prove. What we have seen so far, if you have two propositional variable, then how many rows will be there? Tell me, if you have two propositional variable, if you have two propositional variables, like for example PQ, then tell me how many rows will be there if you have PQ? Then there will be total 4 rows. Why 4 rows? What is the reason 4 rows? Tell me. Okay, there will be total 4 rows in truth table. That is same as basically 4 truth value combinations are there. 4 rows in the truth table, that is same as 4 truth value combinations are there. Now why? Okay, what is the reason? The reason is very simple, because remember, P is a proposition. So either it will take this value or it will take this value. It will take one of these two values. Similarly, Q is a proposition. So either it will be true or it will be false. Now, how many combinations are possible? You can see this combination is possible, this combination is possible, this combination is possible, and this combination is possible. Yes or no? I can say 2 multiplied by 2. Okay, because you can see For P, there are two choices. For Q, there are two choices. Correct. P has two choices. Either it will be true or it will be false. There are two choices for P. There are two choices for P. Either it will be true or it will be false. Similarly, there are two choices for Q. Either it will be true or false. Two choices for Q, two choices for P. So finally, we will get 2 into 2, that is 4. 2 multiplied by 2, these many rows. Okay, you can see FF, FT, TF, TT. So total 4 rows will be there. Or I can say 4 truth value combinations will be there because every variable has two choices. Okay, so you can see 2 multiplied by 2, these many combinations are possible. Now, if you have n propositional variable, then what will happen? You have n propositional variable like P1, P2, okay, and so on, Pn. Now, in this case, you can see how many rows will be there. Very simple point. Every variable has two choices. Every variable, whichever variable you take Pi, that has two choices. Either it will be true or it will be false. So there are two choices for every variable. This variable has two choices. This variable has two choices. Every variable has two choices. Similarly, I can say that this variable also has two choices. Okay, because every variable has two choices, so number of rows that will be number of rows will be 2 multiplied by 2 multiplied by and so on multiplied by 2. Okay, every variable has two choices, so n times, yes or no, n times, so 2 power n, these many rows, these many truth value combinations are possible. You can notice, if you have three variables, then 2 power 3 equal to 8. 8 rows will be there. Okay. So very simple point. If you have three variables, if you have n equal to 3, then you can notice 2 power 3, that is 8. 8 rows will be there. If you have n equal to 2, then we have already seen that 2 power 2, that will be 4 rows will be there. Okay. So if you have n, then there will be 2 power n rows. Very simple. Now let's move on. Now let's see logical laws. Some logical rules are there. Actually, we are already using these rules, but now let's study them formally. Okay. So let's study all the logical rules in propositional logic. Okay. So let me start with very simple rules. You tell me what will happen if I do double negation. P negation again negation. What I will get? Tell me what I will get. I will get P. Okay. This is very simple. You can easily see. Okay. Can you prove it? See, very easily you can prove it. You know that P, if P is true, P is false. Okay. Then what will be P bar? What will be P bar? P bar will be false comma true. Now if I again do, see, let me call it Y. 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 Okay, this I am calling it Y. Then what is Y bar? Y bar is same as P bar double bar. Okay, yes or no? Now you can notice. If this is Y, then what is Y bar? If this is Y, then Y bar will be true comma false. So did you notice this and this, they are same? Yes or no? Okay, this and this, they are same. They are same. So I can say this is same as P. Okay, so like this. Very simple point that if you do double negation, you will get P itself. Okay, very simple point. Let's see another, some easy ones. Let's see. For example, what will be P or true? Tell me, what will happen if you do P or true? That will be true. Okay, you can check the truth table. Okay, just check the truth table of disjunction. Check the truth table of or. You will see that if you do anything or true, that will be true. Okay, similarly, you tell me, if I do anything or false, what I will get? Anything or false, that will be false. Okay, very simple point. Okay, so remember, anything or true, that will be true. Anything and false, that will be false. You can check the check the truth table of and. There you can easily see anything and false, that is always false. Okay, is this clear? Let me tell you, these two rules, they are called domination laws. Why? Can anyone tell me why they are domination laws? This is the name for these two rules. Anyway, the name is not important. This is the name. Why this is the name? Because you can see this true will dominate or operation and false will dominate and operation. Yes or no? True is dominating the or operation. Okay, remember this true. This is dominating the or operation because true or anything, that is true. So true is dominating the or operation. and false is dominating the AND operation, because remember, false and anything is equal to false. So that is the reason these two rules are called domination laws, because true is dominating the OR operation, false is dominating the AND operation. You can see true or anything is true, false and anything is false. So that is the reason this is the name, domination laws. This name is not important, don't worry. Okay, let's see some more rules. You tell me, if I do P or false, then what I will get? And if I do P and true, what I will get? Let me know. You can check the truth table of OR operation, check the truth table of AND operation. If you do P or false, then you will get P itself. Okay, this will be same as P, and you can see P and true, that will be same as P. Okay, these are very intuitive. There is nothing here. For example, let me tell you how to prove it. See, if you want to prove P and false, sorry, P or false, let me prove P or false. What should I write here? What should I write here? See, this is very easy. Tell me, this is fixed, right? This is fixed. Yes, this is a fixed. Okay, this is fixed. So you tell me, this is very easy. Notice, because this is fixed, so P can be false or P can be true. If I put P equal to false, then in this box, what I will write? If I put P equal to false, then in this box, what I will write? False or false, that is false. If I put P equal to true, if I put P equal to true, then in this box, what I will write? True or false, true or false, that is true. So did you notice? Whatever P is, the same thing I am writing in the box. If P is false, I'm writing false in the box. If P is true, I'm writing true in the box. So can I say in this box, I'm writing P as it is? Okay, so anyway, but these are very intuitive. These are very simple. So P or false, that will be P. And P and true, that will be P. Okay, and this is your proof. Now let's see the next one. What is the fourth one? That is, tell me what is P or P bar. If I do P or P bar, what I will get? If I do P and P bar, what I will get? Let me know. If I do P or P bar, what I'm going to get? That will be true. Yes or no? Because one of them will definitely be true. Agree? If P is false, then P bar will be true. Okay. And if this is true, then also this will be true. One of them will definitely be true. One of them will definitely be false. So P and P bar will be false. P and P bar, that is going to be false. Okay, so these are some of the rules. I hope all the rules are clear to everyone. Now, let me ask you some more rules. Okay, simple, and you tell me the answer for these also. You can see some more. You don't have to remember them. Do not remember them. Okay, just tell me the answer. For example, if I ask you what is P implies false, what this will be? P implies false. Tell me what it will be. P implies false. See, you can easily prove it. Okay, let's see. You already know that alpha implies beta. That is same as what? That is same as alpha dash or beta. Yes or no? Alpha dash or beta. So tell me, what is P implies false? P implies false. That is same as P bar or false. Now remember, alpha or false, that is alpha. So this will be P bar. So finally you will get P bar. Yes or no? So here what you will get? You will get P bar. Is this clear? Tell me, is this clear? Very simple. So you are going to get P bar. Okay, very simple. So this is how you can do. Let me tell you another method. Let me tell you another method. See, like this also you can think. P implies false. Okay, in this box, what should I write? Remember this false. This is fixed, right? This is fixed. This is false. Okay. So you tell me in this box, what should I write? Remember, if P is false, then in this box, what I will write? If P is false, false implies false. If P is false, false implies false. That is true. If P is true, if P is true, now tell me, if P is true, in this box, what I will write? If P is true, true implies false is false. So did you notice that? If P is false, in the box I'm writing true. If P is true, in the box I'm writing false. In the box I'm writing opposite of P. Yes or no? Did you notice? Okay, if P is false true, then in the box I'm writing true false. Means in the box I'm writing opposite of P, that is P bar. So very simple, that P implies false, that is P bar. Okay, anyway, so very simple idea that this will be P bar. You tell me the next one, that is P biconditional false. Now what it will be? Tell me. P biconditional false. Again, the same idea. You see, this is fixed. This false is fixed. Now you think about P. If this is false, what should I write here? Tell me, if this is false, what should I write here? If P is false, then biconditional will become true. Okay, yes or no? And if P is true, then this will be false. So here I will write opposite. Okay, yes or no? Did you understand? Very simple point. This is the simple point. I want to know what is P biconditional false. What should I write in this box? Okay, very simple point. This false is already fixed. That you know. That is fixed. Okay, so if P is true, in the box what I will write? If P is true, true biconditional false, that will be false. And if P is false, false biconditional false, that will be true. Okay, so did you notice? I'm writing opposite of P. In the box, I'm writing opposite of P. Because when P is true, in the box, I'm writing false. When P is false, in the box, I'm writing true. So in the box, I'm writing opposite of P. Is this clear? You tell me quickly, what is P exclusive or true? What that will be? Tell me. The same method you can apply. Remember, this is already fixed. Tell me, if P is false, what should I write here? If P is false, I will write true. And if P is true, I will write false. So again, I'm writing opposite of P. You don't have to remember these things. Just understand these things. You don't have to remember these things. For example, what will be P by P XOR false? Let's prove it. P XOR false. What should I write in the box? Tell me, what should I write in the box? This is already fixed. This is already fixed. So now you tell me. Very simple point. Tell me, if P is false, what I will write in the box? If P is false, then false exclusive or false, that will be false. And if P is true, then it will be true. So can you see, I'm writing P as it is. I'm writing P as it is. Okay, so this will be same as P. I hope all these points are clear. Let me know. Understood? So can you solve all these type of simple equations? Can you do this type of simple equations? For example, tell me, if I ask you, what is true biconditional or maybe false biconditional P? Tell me what this will be. False biconditional P. Let me know. This will be P bar. You can check it. Okay, whatever you write here, the opposite will come. Whatever you write here, the opposite will come. So very simple. Okay, so like this. Anyway, I hope all these points are clear. Let me know. If P implies true, what that will be? P implies true. That will be same as true. Okay. Remember, for implication, just remember this rule. Alpha implies beta. That is same as alpha bar over beta. Okay. So remember, if this RHS is true, then entire thing will be true. Similarly, remember, if you have false implies P, what I will get? If this is false, if LHS is false, then the entire thing will be true. Okay, just remember this rule. Using this rule, you can solve it. Very simple. Okay. And one more thing I can say, that is P implies false. That will be what? That will be P bar. Okay. You can see, just apply this. Alpha implies beta equal to alpha bar or beta. Just apply this. Only apply this. That's it. And finally, I can say true implies P. That will be same as P. Okay. So that's it. Now let's move on. All these rules we have seen, you can check it out. Okay. The names are not important. Don't worry about the names. Now let's see. Let's see the next rule, that is commutative law. This name is actually important. Commutative. Okay. So let's see what is this commutative law. First, let me tell you the general definition of commutative law. When can you say some operation is commutative? Commutative operation. When can I say that some operation is a commutative operation? So if you have an operation, let's assume hash. Okay, any operation. You can have AND or XOR, any operation. Let's assume you have operation hash. So when can I say this operation hash? Okay, this operation hash is commutative. This operation hash, this is commutative. What is the definition of commutative? This is commutative if and only if, very simple point, that A hash B, that will be same as B hash A. Okay, A hash B, that will be same as B hash A for all A comma B. Whatever A comma B you take, for all A comma B, whatever A comma B you take, this A hash B should be same as B hash A. Basically, this is the commutative rule that you can change, you can basically swap their places. Okay, A hash B equal to B hash A. Do you remember in mathematics, do you remember some commutative operation in mathematics, in your regular mathematics, in number theory, in arithmetic? Do you remember in arithmetic what is commutative operation? We know that addition is commutative, right? A plus B is equal to B plus A. Yes or no? So you can notice that for all A comma B, whatever A comma B you take, addition is commutative. So can I say addition is commutative? Addition operation is commutative. Similarly, multiplication operation is also commutative. B multiplied by A equal to A multiplied by B. Okay, for all A comma B, whatever A comma B you put. So again, I can say that multiplication is also commutative. Multiplication is also commutative. What about subtraction? Tell me, what about subtraction? Can I say A minus B is same as B minus A? Can I say A minus B is same as B minus A? No. So subtraction is not commutative. So subtraction is not commutative. For example, 2 minus 3, that is not same as 3 minus 2. So subtraction is not commutative, but addition, multiplication, they are commutative. So did you understand the definition of commutative operation? Commutative means this operation has is commutative if A has B equal to B has A for all values of A comma B. Whatever A comma B you put, this equation will satisfy. Okay. Now you can easily see which operations are commutative in propositional logic. In our propositional logic. Okay, you can easily see in our propositional logic, or is commutative, P or Q, that will be same as Q or P. Okay, so or is commutative. Next, you can see and is also commutative. P and Q, that is same as Q and P. Okay, so or comma and, they are commutative. In propositional logic, these operations are commutative. These are called commutative laws. These are called commutative laws. Okay, very simple. That and comma or, they are commutative. A and B equal to B and A or B equal to B or A. Okay. Tell me the answer for this question. Which other operation is commutative? In propositional logic, which connective is commutative? Let me know. Which of them is commutative? You can see and is commutative, or is commutative. Let me tell you, implication is not commutative. Okay, because P implies Q, Q implies P, they are not same. In the last lecture, we have already seen P implies Q, Q implies P, they are not same. Biconditional is commutative, XOR is commutative, NAND is commutative, NOR is commutative. Okay, you can easily prove anything. For example, let me see, what about implication? Tell me, what about implication? Implication is not commutative, right? Yes or no? Implication is not commutative. What it means? It means that P implies Q, Q implies P. They are not same. This we have already seen in the last class. P implies Q. This is not same as Q implies P. Okay. Can you give me a situation where they will give you different truth value? Can you give me a situation where they will give you different truth value? This P implies Q, Q implies P, they will give you different truth value. Yes, you can consider when P is true, Q is false. In this case, what will happen? In this case, P implies Q will become false, but Q implies P, that will become true. So you can notice that these two, they are not equivalent. Yes or no? In this case, they have different truth value, so they are not equivalent. P implies Q, Q implies P, they are not equivalent. Correct? So implication is not commutative. Okay, what about other operations? Let's check. Let's check exclusive or any other operation. For example, you can check XOR. Okay, you can create the truth table of XOR and you can check. Okay, you can create A XOR B. Just create the truth table of A XOR B. That will be same as truth table of B XOR A. Okay, from the truth table you can easily see this. From truth table you can easily check. Okay, just create truth table of A XOR B, B XOR A. That will be always same, because this will be true when both are different. This will be true when both are different. Okay, yes or no? So order does not matter here. Okay, in the XOR, order does not matter because this will be true when both are different. So same here, this will be true when both are different. Okay, you can see the same thing for NAND. What about NAND? You can check from the truth table, but let's check from the equation. Tell me what is A NAND B and what is B NAND A. NAND means first you do and then you do negation. Yes or no? First you do and then you do negation. Correct? Okay. Here also, what you will do? First you do and then you do negation. We know AB equal to BA. We know AB equal to BA. So they are same. So they are same. Yes or no? Okay, correct. So they are same. So NAND is also commutative. So remember, you can see in propositional logic, you can see other than implication, all the operations are actually commutative. But implication is not commutative. Okay. So this implication, this is not commutative. I hope this point is clear. Okay. Let's move on now. Now let's see the next rule, the next law, that is associative law. What is the definition of associative law? First, let me tell you about the general definition. When do you say that some operation is associative? Associative operation. When can I say that an operation is associative? So the definition is actually very simple. If you have some operation hash, you can take any operation. If you have some operation hash is associative, if and only if, what should happen? Associative means like this. If you do this hash back to back, A hash B hash C, if this hash you do back to back, okay, then remember, whether you first do A hash B or you first do B hash C, this should not matter and the results should be same. Okay, is this clear? So remember, this operation is associative. If whether you do this first or whether you do this first does not matter, both will give you same result. Okay, this should happen for all A comma B comma C. Whatever A comma B comma C you take, this should happen for all A comma B comma C. This equation should always be true. Okay. Now tell me, in your regular mathematics, in arithmetic, do you remember some operation which is associative in arithmetic? Let me know. In arithmetic, do you remember some operation which is associative? Yes, the addition operation, A plus B plus C. Okay, A plus B plus C. Whether you do this addition first or whether you do this addition first, the result will always be same. So addition is associative. Yes or no? The same thing for multiplication. If you do, notice the same thing for multiplication. A multiplied by B multiplied by C. Okay, you can see that whether you do the first multiplication first or whether you do the second multiplication first, the result is always same. Okay, so what about subtraction? What about subtraction? Can I say the same thing for subtraction? Can I say whether you do the first subtraction or whether you do second subtraction first? Can I say they will always give you same result? Can I say they will always give you same result for all A comma B comma C? No. Okay, you can check. You can check. Take A equal to 2, B 3, C 4. Then tell me what will be LHS? Tell me. A equal to 2, B equal to 3, C equal to 4. A equal to 2, B equal to 3, C equal to 4. Now you tell me what will be this LHS and what will be this RHS. So you can easily see this LHS will be minus 5. This LHS will be minus 5. And you can easily see this RHS. This RHS will be what? That will be 3. Yes or no? Is this clear? Okay. So LHS will be minus 5 and RHS will be 3. Is this point clear? Please tell me. Simple. Okay. So addition comma multiplication, they are actually associative. So I can easily say that addition multiplication are associative. Okay. In arithmetic, addition multiplication are associative, but subtraction is not associative. Subtraction, that is not associative. Now you tell me about and comma or. in propositional logic. Let's come to the propositional logic world. So in propositional logic, now you tell me. In propositional logic, this is very simple. You can check it from the truth table. You can create the truth table. P and Q and R. And is actually associative. And comma or both are associative, means P and Q and R. Or if you do like this, they will give you the same result. And comma or both are associative. P or Q or R. You can create the truth table and you can check. This is not a complicated thing. This is very intuitive thing, that and comma or they are actually associative. Yes or no? And is also associative, or is also associative. Both are associative. Okay, so very simple point. You can see and is associative. First to do this or first to do this, you can see the result will be same. Or is associative. Okay, so first to do this, first to do this, the result will be same. Okay, simple. Now, again, my question, in propositional logic, which operator, which connective is associative? Tell me, which of them is associative? We have already seen and is associative, or is associative. What about the remaining? What about the remaining? Let me tell you that implication is not associative, by implication is associative, XOR is associative, NAND is not associative, NOR is not associative. And you can prove all these. For example, let me prove implication. Let me prove implication. That implication is not associative. Implication is not associative. Can you prove it? Basically, what I want to prove that P implies Q implies R. Okay, P implies Q implies R. I want to prove that if you do this first implication first, or if you do the second implication first, I want to prove they can give you different result. These two expressions, they are not equivalent. These two are not equivalent. They can give you different result. Can you give me a situation where they will give you different result? This LHS and RHS, they will give you different result. Can you give me a situation? Let me give you. Take P false, Q true, and R false. Take this. In this case, what will happen? Just check it. In this case, P false, Q true, R false. In this case, what will be LHS? In this case, what will be LHS? Tell me. What will be LHS? If I put P false, Q true, R false. So in LHS, first we are doing false implies true. That is true. So this will be true. Yes or no? This will be true. True implies false. True implies false. That will be false. So LHS will be false. What will be RHS? You can see P is false. False implies anything. That is true. False implies anything. False implies anything. That is true. So did you notice that LHS, RHS, they are not equivalent? You can notice in this case, they have different truth value. In this case, they have different truth value. So you can notice they are not equivalent. LHS, RHS, they are not equivalent. Okay, so I can say this and this, they are not equivalent. So implication is not associative. Is this point clear to everyone? Okay. So very easily, you can see this. And the remaining, I leave it up to you. You can prove it that by implication, XOR, okay, and these operations, okay, you can easily check. Let me check for maybe XOR. Okay, let me check XOR. So what about XOR? XOR is actually associative. Okay, exclusive OR, that is actually associative. Okay, this exclusive OR, this is associative. Okay, so whether you do the first implication, first XOR first, or whether you do the second XOR first, the result is always equivalent. Okay, you can actually prove it with the help of truth table. Okay, so you can just, or you can apply the by case method. If you want, you can apply the by case method. So in the by case method, remember this and this LHS, RHS, they are equivalent. Okay, and you can prove it with the help of by case method. Tell me how many cases are possible? How many cases are possible? Case 1, case 2. Only two cases are possible. Either P will be true or P will be false. There is no other possibility. Yes or no? Only two cases are possible. Now tell me, in this case, when P is true, what will be LHS and what will be RHS? When P is true, just put P equal to true. XOR is associative and you can easily prove it. XOR is associative. Okay, we can easily prove it. So basically we want to prove that LHS is equivalent to RHS. Okay, so you can apply the by case method. Again, this question you can apply the by case method. So very simple, apply by case method to prove, or you can create the truth table. So tell me, only two cases are possible, P true, P false. So if P is true, then what will be LHS? Let's see what will be LHS if P true. True XOR Q XOR R. Okay, so tell me true XOR Q, what is that? We have already seen this. Okay, if you put Q false, then result will be true. If you put Q true, result will be false. So result is opposite of Q. So basically, this is Q bar. Okay, so your LHS, what is that? LHS is Q bar XOR R. Okay, what is RHS? What will be RHS? I am putting P true. Okay, I am putting P true. So what will be RHS? Again, if this is, let's assume this is alpha. For a moment, let's assume this is alpha. What is true XOR alpha? That is alpha bar. True XOR alpha. True XOR alpha, that will be alpha bar. Okay, let's assume this is alpha. This entire thing is alpha. So you can see if this alpha is true, final result will be false. If alpha is false, final result will be true. So the final result is opposite of alpha. Okay, so this will be your alpha bar. Alpha bar means your LHS is what? LHS is Q XOR R bar. Okay, but here you cannot stop. Actually, this and this, they are also equivalent. Okay, this and this, they are also equivalent. Again, you can prove it. Now you can create cases by Q. Okay, this LHS and this RHS, they are also equivalent. They are also equivalent. This is actually a standard property. So you don't have to think that this is taking too much time. No, actually, this is a standard property. We will see after some time that these are standard properties. Okay, so don't worry. But right now, let me prove it that these two are also equivalent. This is LHS, this is RHS, and they are also equivalent. Basically, when you put P equal to true, then LHS is Q bar XOR, LHS is Q bar XOR R, and RHS is Q XOR R whole complement. Okay, and let me prove it that they are also equivalent. Okay, this LHS, RHS, they are also equivalent. So let me just quickly prove it. This is RHS. Okay, so actually they are equivalent. Let me quickly prove this. So what is your LHS? LHS is Q bar XOR R. And what is RHS? RHS is Q XOR R whole complement. Okay, so again, you can create by case. Again, the same method, by case method. Now you can create cases by variable Q or variable R, whatever, that is your choice. So let me create case 1, that is Q true, and case 2, that is a Q false. Okay, so let's see this. When Q is true, what will be this LHS? When Q is true, tell me what will be LHS here? What will be this Q bar XOR R? This will be what when Q is true. So you put Q true means Q bar will be false. False XOR R. This will be false. What is false XOR R? You can see this is same as R. False XOR R, that will be same as R. Okay, you can check it. False XOR R. False XOR R. What should I write in this box? Tell me. False XOR R. Very simple. This is already fixed. This is already fixed. Yes or no? So if R is false, then in this box, what I will write? Tell me. If R is false, then false XOR false, that is false. And if R is true, then false XOR true, that will be true. So did you notice that in this box I'm writing R as it is? In this box I'm writing R as it is. So this is what I'm saying, that when you put Q equal to true, then this expression will become R. What about RHS? What about this RHS? When I put Q equal to true, when you put Q equal to true, then this entire thing, this internal thing, remember, when you put Q equal to true, this internal thing will become R bar. This will become R bar. Then again there is negation. So finally it will become R. So you can see they are same. Yes or no? They are equivalent. What about the case 2? In case 2, what will be LHS? When you put Q equal to false, so this will be true. True XOR R. True XOR R, that is R bar. Okay, and what is RHS? When you put Q equal to false, if you put Q equal to false, then this internal thing, this will become R. And there is complement, so this will be R bar. Again, you got equivalent. Again, they are equivalent. Okay, so very simple point that this expression, they are actually equivalent. This is what we have proven, that these two expressions are equivalent. This expression, they are equivalent. We have proven using by case method. Two cases we created, Q true, Q false. So finally, this is the result we got, that these two are actually equivalent. Okay, these two, they are actually equivalent. Okay, they are equivalent. Is this clear? And what about case 2? When P is false, then what will be LHS? What will be RHS? Tell me what will be LHS? When P is false. So if P is false, if you put P false, then this will be Q bar. Okay, this will be Q bar XOR R. And what will be RHS? When you put P equal to false, if you put P equal to false, let's call it alpha. If you put P equal to false, it will be alpha as it is. Okay, it will be Q XOR R. Okay. So if you put P equal to false, here you will get, sorry, Q XOR R. Okay. If you put P equal to false, this will be Q XOR R. This also will be Q XOR R. And they are same. Yes or no? They are same. Is this clear to everyone? Please tell me. If you put P equal to false, let's put P equal to false. What is false XOR Q? What is false XOR Q? See, this is very simple. You don't even have to take copy pen. This is actually very simple, because this is false, this is fixed. Okay, yes or no? Now you can easily see that if this Q is false, if I put Q equal to false, the final result is false. If I put Q equal to false, then false XOR false, that is false. If I put Q equal to true, then this false XOR true, that will be true. Okay, so you can notice that this Q as it is, I'm writing in the box. Okay, this Q as it is, I'm writing in the box. So this is what I'm saying, that in this case, when P is false, then you can see when P is false, then this will be Q. This will be Q. So it will be Q XOR R. LHS will be Q XOR R. And you can see RHS also will be Q XOR R. They are equivalent. So did you notice that in both the cases, LHS, RHS are equivalent? Is this clear? Our main objective is we want to prove that this XOR is associative. This is what we want to prove, that XOR is associative. Okay, to prove it, basically we need to prove that LHS and RHS, they are equivalent. This is what we need to prove. Okay, that this expression and this expression, they are equivalent. And we are proving by case method. Two cases we created, P true, P false. Okay, you can see this case is very simple. In this case, what will happen? You will get these two, and you can easily prove that they are also equivalent. Actually, this is a standard result, so you don't have to worry. Okay. After this lecture is over, this standard result also you will know. So this question will become very easy for you. But anyway, I have shown you how to solve. Okay, how to prove, how to solve. I have given you the complete explanation. I have given you. Okay. So did you notice that only two cases are possible, P true, P false? In both the cases, LHS, RHS are equivalent. In this case also, LHS, RHS equivalent. In this case also, LHS, RHS are equivalent. So I can say in all the cases, this LHS and this RHS, they are equivalent. So this XOR is associative. And this is also a standard result. In the GATE exam, you don't have to prove it, because this is a standard result, so you should remember it. But if you forget, if you don't know, then you can do like this, or you can create the truth table. Okay, but truth table is actually very time taking. Okay, it will be actually very time taking, so you can do like this, very easy. Is this clear? Let me know, please tell me. So XOR is associative. This is what we have seen. Now let's see distributive law. What is this distributive law? And this is also very simple. First, let me ask you, in arithmetic, have you seen this distributive law in your regular mathematics, or I can say in arithmetic? In arithmetic, have you seen this distributive law? For example, have you seen that When I do A multiplied by B plus C, what I get? A multiplied by B plus C, we get AB or AC. This is what you do, yes or no? Actually, this is distribution. What you are doing, you are distributing. Actually, it is like this: A multiplied by B plus C. So here, this operation you are distributing. This operation you are distributing. What you are doing? You are doing A multiplied by B plus A multiplied by C. Okay, this is what you are actually doing. Is this clear? So we have this property in our mathematics, in regular mathematics, in number theory, or I can say in arithmetic. A multiplied by B plus C, that is AB plus AC. Yes or no? So I can say that multiplication is distributive over addition. This is what I can say. I can say that multiplication is distributive. We can distribute multiplication over addition. Multiplication is distributive over addition. Okay, you can see multiplication, that is distributive over addition. So this is what we can say. Okay, you tell me, in arithmetic, can I say addition is distributive over multiplication in arithmetic, in your regular mathematics? Tell me, let me know. In arithmetic, can I say addition is distributive over multiplication? Can I say addition is distributive over multiplication? The answer is no. The answer is okay. Addition is distributive over multiplication. The answer is no. Okay, for this question, the answer is no. Why? Okay, you can easily see. See, in your school life, you have seen this. Can you do this? That if you have A plus BC, can I do A plus B, A plus C? Can I do this? Tell me, can I do this? No, I cannot do. Yes or no? I cannot do. Okay. So, very simple point, that addition is not distributive over multiplication. Okay. But multiplication is distributive over addition. So, this is the distributive property. I hope you understood. These are the examples from your school life. Okay. Now, let's see the general definition of distributive property. Distributive property. Let's see the general definition. Let me tell you one thing. In GATE 2024, there is a question based on distributive property where you have to see, you have to apply the distributive property definition. Okay, they have given you a question in which you have to apply the definition of distributive property. Okay, so let's see the distributive property definition. So for distributive property, you need two operations. Do you agree? See here, multiplication, addition. Yes or no? For distributive property, we need two operations, multiplication, addition. So we need two operations. So very simple point. If you have operation, if you have operation has is distributive. Operation has is distributive over star if and only if. Okay, means this is some operation, this is some operation. Has is distributive over star if and only if this equation, look at this equation. Okay, when you have this, then hash is distributive over star. What that means? That means what you can do, you can distribute this hash, you can distribute over star, means you can write as a hash b star star a hash c. Okay, is this clear? Basically, a hash b, a hash c. Okay, so like this. So for all a comma b comma c, for all a comma b comma c, whatever value of a comma b comma c you take, this equation should satisfy. This is the definition of distributive property. Is this clear? Operation hash is distributive over star. What it means? It means a hash b star c, that is equal to a hash b star a hash c. Okay, this is the definition of distributive property. Now let me tell you, in propositional logic what happens. In propositional logic, let me tell you, or is distributive over and is distributive over or. Both are distributive over each other. In propositional logic, okay, in propositional logic, both are distributive over each other. Means you can distribute and over or. Okay, and p and q or r, that is equal to pq or pr. Okay, so and is distributive over or. Also, or is distributive over and. Or is distributive over and means you can also write it P or Q and P or R. Okay, is this clear? Remember, basically, this is or, this is not addition, this is not multiplication, this is and. Are you getting my point? What I'm saying, I'm saying P or Q and R, that is same as you can distribute or over and, you can also distribute and over or. Means in propositional logic, or is distributive over and is distributive over or. Both are distributive over each other. Okay, so you can see if you have P or Q and R, then you can write it P or Q, P or Q and P or R. Okay, P or R. So like this, very simple. So these are the properties. Remember that these two operators and comma or, these two operators, they distribute over each other. Means A and B or C, that is same as A and B or A and C, A and B or A and C. Similarly, A or B and C, that is same as A or B and A or C. Okay, very simple. So remember these two operators, they distribute over each other in propositional logic. Okay, very simple point. So in propositional logic, remember, you can do this. In propositional logic, you can do what you can do in propositional logic. In propositional logic, you can do this. For example, if you have P, Q and R, Q and R, sorry, P, P, Q plus R, then remember you can write it like this: P and Q or P and R. Okay, like this. You can also take common. For example, if you have PQ or PR, you can take P common, means P and Q or R. Okay, so these things you can do in propositional logic. In propositional logic, we can do these things. So if you have PQ or PR, so you can write it P and Q or R. Okay, is this clear? Are you getting my point? What this actually means? This means P and Q, P and Q or P and R. So what we can do, we can take P out, P common. So P and Q or R. Okay, so like this. Anyway, in short, you can write like this because I told you that this means and. PQ means P and Q, and this means or. In propositional logic, this means or, and this means and. Okay, so in propositional logic, you can take common also. Very simple. Now let's see the next law, the next logical rule, that is De Morgan law. Okay, and this is very simple. What this De Morgan law says, let me tell you. De Morgan law is very simple. This says that if you have P and Q and you do its negation, P and Q negation, then what you will get? Then that is same as what you do. You do P bar, this and will become or, and this Q will become Q bar. Very simple. Okay, similarly, P or Q, if you do negation, what you will get? Again, this P will become P bar, this or will become and this Q will become Q bar. This is called De Morgan law, and you can very easily prove it. See, the proof is not complicated. If you want, you can prove it. Let's prove. Okay, prove that. If I ask you, let's prove that P or Q whole negation is same as P negation and Q negation. Then how to prove it? You can create the truth table, or you can create the by case method. Okay, or you can create by case method. So let's use the by case method. Two cases are possible. What is case one? That is P true. And what is case two? That is P false. So tell me, when P is true, what is LHS? What is LHS? What is this LHS? And what is RHS? Let me know. When P is true, when P is true, this internal thing will become true. When P is true, this internal thing, this will become true. Negation of true will be false. Okay, negation of true, that will be false. So LHS will be false. Okay, when P is true, then what will be RHS? When P is true, then this will be false. False and anything, that is false. Okay, so RHS is also false. So you can notice they are same, they are equivalent. What about case 2? When P is false, then what will be LHS? What will be RHS? When P is false, Okay, just put P equal to false. So this internal thing, this will become what? When you put P equal to false, so false or Q, that will be Q. So finally Q negation, it will be Q negation. And remember, when you put P false in this RHS, then this will become true. True and alpha is alpha. True and alpha. True and alpha is alpha. So true and Q bar is Q bar. So did you notice that they are also equivalent? So one thing you notice that only two cases are possible. In both the cases, LHS, RHS are equivalent. In both the cases. In case 1 also, LHS, RHS are equivalent. In case 2 also, LHS, RHS are equivalent. In all the cases, LHS, RHS are equivalent. So they are always equivalent. Okay, this is the proof. So very easy. This is the De Morgan law. Okay, De Morgan law means if you have A or B negation, negation of A or B, that is same as A negation and B negation. Basically, this or will become and, A will become A bar, B will become B bar. Similarly, A and B negation, that will be A negation, B negation, and this and will become or. Okay. So actually, what happens? Let me tell you. In De Morgan law, this is actually very simple. De Morgan law is like this. De Morgan law, that is very simple. That simply says that if you have some expression, let's assume you have some expression H. Okay, in this expression H, let's assume you have P, you have P bar, okay, you have Q, you have Q bar, these things you have. Okay, let's assume you have true, you have false, you have and, you have or. These things you have. Then De Morgan law says that if you want H bar, then how to find H bar? To find H bar, what you need to do? Remember, this is H. This is H. Okay. Now, De Morgan law says that if you want to find the complement of this or negation of this, if you want to find the negation of this, then what you need to do? Very simple. This P will become P bar. P bar will become P. Q will become Q bar. Q bar will become Q. Okay. Very simple. Just complement everything. Just negate everything. This true will become false. This false will become true. Okay. And will become or will become and. Okay. Is this clear? Let me know. So, for example, let's assume that you have this expression H, and H is like this: P bar or Q and P and Q. Okay. So let's assume this is H. Then what will be H complement? H negation. H negation will be what? H negation will be what? If this is H, here you can notice what you have. Here you have and, here you have or. These things you have P, Q, and or. So if you want H negation, then very simple. What you need to do? This and will become or. Okay, this and will become or. This P bar will become P. This P bar will become P. This or will become and. This Q will become Q bar. This P will become P bar. This and will become or. This Q will become Q bar. Remember, this and will become or. So like this. This is a H negation. This is negation of H. Okay, so this is De Morgan law. Remember that if you have H, this is your expression. In this expression, you have these things: P, P bar, Q, Q bar, true, false, and or. If these things you have in the expression, these things you have in your expression, then how to find the negation? How to find the negation? Very easy. P will become P bar, P bar will become P, Q will become Q bar, true will become false, false will become true, and will become or will become and. Okay, so like this. And you can see this is the example. So that's it. Now, the next law, the next rule, that is absorption law. And this is very useful. This is actually very useful. Absorption law. What this law says, and very easily you can prove it. This absorption law is like this. You will see why we call it absorption law, because it will absorb. See, this absorption law says that P or PQR, basically P or PQ. Okay, P or PQ. Yes or no? P or PQ. P or PQ. Then here, this will be same as P. Means this P will absorb anything where you have P, Q, R, whatever. Okay, so this is P or PQ, that will be same as P. Okay, very simple. This is the absorption law and this is very useful. Okay, let me prove it. Let's see the proof. What is the proof? See, the proof is very simple. You can apply the by case method, or you can just take common. See, P or PQ. What you do? You just take common. Can I write it P and 1, P and true, P and true, or PQ? Can I write like this? Can I write like this? Because what is P and true? P and true, that is P. Yes or no? P and true, that is P. P and true, that is P. So now I can take P common. What I will get? I will get true or Q. What is true or Q? What is true or Q? That is true. What is P and true? That is P. So finally I got P. Okay, is this clear? Very simple, right? So like this. So this is the absorption law. So this absorption law is actually very useful. Okay. Now one more useful law, let me tell you. Okay, one more law. Actually, this is another. This is there is no name for this rule, but this is another useful law. Let me tell you that is like this. If you have P or P bar Q, now what will happen? See, P or PQ will be P because here this will absorb. This P will absorb PQ. Okay, so it will be very simple. The proof we have seen. But if you have P or P bar Q, then what will happen? Let me tell you. Then what you do like this. P or P bar Q, then this P bar you can remove. It will be same as P or Q. It will be same as P or Q. Okay. So like this you can do. Is this clear? Very easily actually you can prove it. Let's see the proof. You can prove it by case method, or you can apply the distributive property. See, you just apply the distributive property. We know the distributive property. Okay, just apply the distributive property. It will be P or P bar and P or Q. Now what is P or P bar? P or P bar, that is true. True and alpha is alpha. So finally you will get P or Q. Okay, here what we have done, we have applied the distributive property. We have applied the distributive property because you already know the distributive property, that is P or P bar Q. So you can apply distributive property. It will be P or P bar, P or Q. Okay, so very simple. Finally, you will get P or Q. So these are useful. Remember, let me give you the final conclusion here that these two rules are actually very useful. One of them is called absorption law. One of them is called absorption law, but actually these rules are actually very useful rules. Okay, the one is your absorption law, that is P or PQ, that is same as P. Another is like this, P or P bar Q. Here you can remove this P bar and you can write it P or Q. Okay, these rules are useful, very useful. Okay, this is called absorption. This rule is called absorption. There is no name for this rule, but these are very useful. Okay, now let's see some more logical laws, few more important rules. Okay, all these rules, these are very simple. Okay, you can easily prove them. If you want to prove them, you can use the truth table or you can use the by case method. Is this clear? Everything that we have seen, every rule, every logical law we have that we have seen, you can prove it with the help of truth table or with the help of by case method. Okay, so everything you can easily prove. Now let me tell you some more important laws that actually we have already seen. If you remember laws related to implication, do you remember some rules related to implication? Do you remember laws related to implication? For example, the first rule related to implication, that was P implies Q, that is same as P bar or Q. Correct? Okay, very simple. Another is P implies Q, that is same as Q bar implies P bar. Yes or no? So these are related to implication. These two rules, they are related to implication. Okay, and these are very useful. Alpha implies beta, that is alpha bar or beta. P implies Q, that is same as Q bar implies P bar. Okay. Now let's see some more. Let's see exclusive OR. Let's see writing exclusive OR. Writing XOR. Writing XOR. Okay, so let's see how to write XOR. Okay, this is actually, just understand, this is actually very simple. Notice, very simple. P XOR Q. You tell me when it will be true. Just tell me when P XOR Q will be true. You just tell me P XOR Q when this will be true. Let me know. Let me know when this will be true. P XOR Q when this will be true. This will be true if and only if and only if either this happens, P true, Q false, P true and Q false. Either this happens or this happens, P false, Q true, P false and Q true. Do you agree with me? Tell me yes or no. Okay, remember P XOR Q, that is true. Either this should happen, P true, Q false, or this should happen, P false, Q true. Yes, agree? So far, you agree with me? P XOR Q. This is true. When this XOR is true, this XOR is true when they are different. XOR is true when they are different. When they are different, means either this should happen or this should happen. Okay. P true, Q false, or P false, Q true. Now you can easily write it. Now let's see how to write it. Now see, just see, very simple. So this P XOR Q, you can write like this. Notice, OR means OR. Yes or no? OR means OR. This is your OR. Okay, so you got OR. Here there is AND. P true, Q false. How to write Q false? In the last lecture, I told you, if you want to write Q is false, then how to write it? If you want to write Q is false, how to write it? That is negation Q. Yes or no? That is negation Q. Agree? In the last lecture, we have seen, I told you, many different interpretations of negation. How to read this? Okay, it is not the case that Q, it is not true that Q, it is false that Q is false. Okay, yes or no? So Q is false. That is same as Q bar. This is how we write. In the last lecture, we have already seen. So very simple. P true and Q false. So how to write it? There is and here. P true and Q false. So PQ bar, or, okay, there is a or, P false, P false and Q true. Okay, that means P bar Q. Is this clear? Did you understand how to write exclusive OR? Let me know. Let me know. Did you understand? Yes or no? Simple, very simple. So this is your OR here. You can see. Okay. So like this, you can write. Okay. Very simple. Remember, XOR, you can write like this. Basically, from now onwards, P XOR Q, that is same as basically P bar Q or PQ bar. Okay. P bar Q or PQ bar. P bar Q or PQ bar. Understood? Now you can easily see all the things. For example, now you can see what will be, tell me, what will be true XOR Q? What that will be? Just apply this rule, apply this equation. What will be true XOR Q? That will be very simple. That will be true bar Q or true Q bar. Okay, yes or no? True bar Q, that is false, and Q, that is false. This will be false. This will be Q bar. What is Q bar or false? What is Q bar or false? Q bar or false? That is Q bar. So you got Q bar. Yes or no? So very simple, right? Now whatever you want, you can do. Okay, agree? So very simple. One thing I want to tell you, that this true, you can also write it 1. Okay, this false, you can also write it 0. Okay, actually, this is what we use in propositional logic, and this is what we use in Boolean algebra. Okay, so when we study propositional logic, we use true comma false. When we study propositional logic, we use true comma false. And in digital logic, there is a topic that is Boolean algebra. Maybe you have seen in your school life, in your college life, Boolean algebra in digital logic. There we use 0, 1. Okay, so these things we use in Boolean algebra, but they are actually same. Basically, true, you can write 1, false, you can write 0. Okay, both will be same. Is this point clear? Okay, so very simple. True, that is same as 1, and false, you can write it 0. Okay, very simple point. Now, so tell me, what will be 0 XOR Q? What that will be? 0 XOR Q. Just apply this equation. Okay, that will be 0 bar Q or 0 Q bar. 0 means false. 0 means false. False and Q bar. That will be false. Okay, and this will be Q. So finally, you will get Q. So this is how you can write XOR. Did you understand writing XOR? Did you understand? Now let's see how to write biconditional. Writing biconditional. And this is also very easy. Similarly, you can write biconditional. Tell me how to write biconditional. You already know when this biconditional will be true. This biconditional, when can I say this will be true? Let me know. Biconditional is true if and only if biconditional is true if and only if either this should happen or this should happen. Remember, biconditional is true if they are same. Biconditional is true when PQ are same. Means when P true Q and Q true, or P false and Q false. Agree? Yes or no? So this biconditional, this will be true if this happens or this happens. Okay, P true, Q true, or P false, Q false. Now can you write equation? Now can you write equation P biconditional Q? Can you write the equation now? Now you have become expert. Okay, this or, this is your or, very simple, this is or. Now, P true and Q true, that is PQ. P true and Q true, that is PQ. P false and Q false, that is P bar Q bar. P bar Q bar. So that's it. So this is the equation for biconditional. Is this clear? Okay, let me know. Is this clear? Biconditional equation. So remember, P biconditional Q. Okay, this is the equation that this is same as PQ or P bar Q bar. Okay, this is the equation for biconditional, and this is the equation for XOR, P bar Q or PQ bar. So these are the different equations we have seen. And how to write them, did you understand? Will you ever forget? Will you ever forget? Just understand the logic. I've given the logical proof. I've given you the logical explanation of these equations. Okay. So that's it. We have seen all the logical laws. Every logical law we have seen. We have seen what is P and true, that is P. What is P or false, that is P. P or true, that is true. P and false, that is false. P or P, that is P. P and P, that is P. Okay. Remember, P or P, that will be P. P and P, that will be P. Yes or no? Next, you can see P double negation, that is P. Commutative law we have seen, and comma or they are commutative. Associative law we have seen, and comma or they are associative. Distributive law we have seen, and comma or they are distributive over each other. And is distributive over or is distributive over and. We have seen De Morgan law, we have seen absorption law. Okay, next you can see all these rules we have seen. We have seen this rule, P implies Q is same as P bar or Q. We have seen P implies Q is same as Q bar implies P bar. Okay, so everything we have seen. We already know this. P double implication. This is your by implication. So P by implication Q, that is P implies Q and Q implies P. This also we already know. In the last lecture, we have already seen this. Okay. So these are all the logical rules. Please tell me, did you understand each and every logical rule? Did you understand? Let me know. Now let's see what is simplification method. This is another way to solve question. So far what we have seen, to solve question, either you can use truth table or you can use by case method. Okay, but there is another method, that is simplification method. In this simplification method, what we do, we use the logical rules, all the logical laws that we have seen, all the equations that we have seen, we use the logical laws to solve the questions. Okay, so this is your simplification method. So remember, so far what we have seen, To solve question, if you want to solve questions, then you can use truth table, but this is inefficient, boring method, so never use it. You can use by case method, or you can use simplification method using logical laws. All the logical rules that we have seen, all the equations that we have seen, using them you can do the simplification. Okay, so remember, on some questions this is useful, on some questions this is useful. Okay, on some questions this will save a lot of time, on some questions this will save a lot of time. So you just become expert of this and this both. Then depending on the question you can apply whatever you want to apply. We have already seen by case method, a lot of practice we have done. Now we will see simplification method. Okay, let's start with this question. Is this tautology? We need to prove that this is tautology. Now what you can do, you can do this using two methods. Yes or no? Using two methods, tell me. Either you can use by case method or you can use simplification method. So let me use the method one, that is by case method. Okay, first I will apply the by case method, then I will apply the simplification method. Okay, so by case, let me solve this question by case method. Two cases are possible, either p will be true or p will be false. There is no other possibility, only two cases are possible. Now you tell me, let's call it h. This expression, let me call it h. So tell me, when p is true, what will be h? When p is true, let me know what will be h. When p is true, then this will be false. False and anything will be false. False implies q will be true. Yes or no? See, just put p equal to true. If you put p equal to true, then this will be false. P bar will be false. False and anything will be false. False implies anything will be true. False implies anything will be true. So h will be true. When p is true, then h will be true. Now let's see. When p is false, then what will be h? When p is false, just put p equal to false. If you put p equal to false, p bar will become true. True and true and inside what you have? Inside you have put p equal to false. So false or q, false or q, that will become q. Yes or no? Implies q. So what will be h? True and q, that will be q. Q implies q. What is q implies q? Q implies q, that is q bar or q. Yes or no? Q implies q. Q implies q. Remember, alpha implies beta. Remember, alpha implies beta. That is same as alpha bar or beta. So here you can see that q bar or q, that is same as true. That is true. So again, you can notice that in both the cases h is true. Yes or no? In both the cases h is true. When p is false, h is true. When p is true, h is true. H is always true. Yes or no? So h is a tautology. H is always true. Because h is always true, so h is tautology. Very simple. Now the same question you can solve by simplification method also. Okay, so let me apply the simplification method. In the simplification method, what we are going to do? We are going to apply the logical laws that we have seen. All the rules that we have seen, we can apply them. Okay, so you can easily see. Just apply this rule. Alpha implies beta is same as alpha bar or beta. Okay, just apply this rule, alpha bar or beta. So let's apply this rule. What is your equation h? H is actually p bar, p or q implies q. This is h, right? Yes or no? This is our equation h. This is h. P bar and p or q implies q. Okay, so what you can do? Notice, first let's solve it. Okay, first let's solve this. So what you can do here, you can apply the distributive property. Okay, tell me, if you apply the distributive property, what this will become? Can you tell me what this will become? If you apply the distributive property, p bar, p or q, just apply the distributive property, it will be p bar p or p bar q. Okay, what will be p bar p? That will be false. That will be false. Yes or no? So false or alpha, that is alpha. This is alpha. False or alpha, that is alpha. So you will get p bar q. Okay, yes or no? So remember, here you got p bar q implies q. This is finally you got p bar q implies q. P bar q implies q. Okay. Now here you can apply this equation. Alpha implies beta equal to alpha bar or beta. So now you can do this. Okay. So what will happen? You can see alpha bar means PQ bar, PQ bar. Okay. PQ bar or beta. That is or Q. Okay. So finally what you got? Tell me. You can apply the De Morgan law. Yes or no? De Morgan law. Do you remember? What is De Morgan law? De Morgan law was like this. You have P bar Q, okay, P bar and Q whole bar. That will be what? P bar Q whole bar. Just apply the De Morgan law. There is and here. So it will become or. Yes or no? This P bar will become P or Q bar. Okay, yes or no? P or Q bar. So it will become P or Q bar. Okay, and there is or Q here. There is or Q. So finally, what it will become? Remember Q or Q bar, that is true. Q or Q bar. What is that? Q or Q bar, that is true. Okay, and remember true or anything. True or anything is true. Correct? So you can see this Q or Q bar, this will be true. True or anything, true or P, that will be true. So finally you got true. Is this clear? So for this expression H, finally you got true. Is this point clear? Let me know. When you simplify this one, when you simplify this, then finally what you are getting true. Okay, so finally you are getting true. This H is finally becoming true, means this H is always true. So H is tautology. Okay, so let's move on. So tell me, did you understand both the method, by case method, simplification method? Did you understand both the methods? Okay, so depending on the question, can you solve the question by any of these methods? Let me tell you, on some questions, simplification method will be beautiful, or I can say simplification method will save a lot of time. And on some questions, by case method will save a lot of time. Okay, with practice, with experience, you will find out just by looking at the question. When you see the question, you will know that okay, which method I should apply. Should I go for simplification method? Should I go for by case method? Let me give you one guideline. Okay, from a suggestion from my side. If you have a complicated expression, then which method you will apply? If you have complicated long big expression, then you can apply by case method. And if you have a small expression, simple expression, okay, simple cute expression, then you can apply simplification method. Okay, so this is just a suggestion. Now let's do some more practice. Let's solve this question. Is this tautology? Is this not a tautology? Tell me quickly. Okay, for this question, let me apply the simplification method. Okay, so let me quickly do simplification method. Means basically what I will do, I will apply the logical laws that we have seen. Okay, so let's apply them. You already know which rule to apply. You know that alpha implies beta, that is same as alpha bar or beta. Just apply this rule. Okay, just apply this rule. So this will become q bar or p. This will become q bar or p. Q bar or p. There is or here. There is or here. What this will become? What this will become? This will become q or p bar. This will become q or p bar. Yes or no? So finally, what you got? You got q bar or p or q or p bar. Now this is very simple. Okay, you can write it like q bar or q, p or p bar. So finally, you can see that this is a true. Yes or no? True or anything is true. So very simple. For example, this is also true. Yes or no? This is also true. Similarly, this is also true. True or true, that is also true. So finally you got a true. Means remember this expression, this entire expression that you have, this expression is basically finally it is becoming true. Okay, means it is always true. So this is a tautology. So the answer will be option A. This is a tautology. Very simple. Let's solve this question. Using the logical laws, prove that each statement is tautology. And this is very simple. Okay, you can easily apply the simplification method. Just apply the simplification method. Okay, do you remember alpha implies beta? That is same as alpha dash or beta. Alpha dash or beta. So just apply this. So here, if you apply this, this is your alpha, this is your beta. So what it will become? It will become PQ whole bar. Okay, because this is alpha. So alpha implies beta means alpha bar or beta. Okay, so it will become PQ bar, or this is P or R. This is P or R. Now you can apply the De Morgan law. What will be De Morgan law? Tell me, what is De Morgan law? Do you remember? De Morgan law, that is P and Q whole bar, that is same as P bar or Q bar. This is our De Morgan law, so you can apply this. So P bar or Q bar, or P or R. Now this is very simple. You can take this. Okay, you can take like this: P bar or P or Q bar or R. Okay, what is P bar or P? That is true. Yes or no? True or anything, that is true. Okay, yes or no? P or P bar, that is true. True or anything, that is true. So finally you got true. So option A, that is tautology. Okay, what about option B? Let me know. What about option B? Tell me. Let's check for option B. The same thing you can do for option B. It will be like this, that it will be P implies what this is. This is R bar or P. Yes or no? Okay, this is R bar or P. Now, remember alpha implies beta. That is same as alpha bar or beta. Now this will become what? Now this will be P bar, or this will be as it is. Okay, again you can notice here your P, here P bar. So this again it will become true. Okay, very simple. What about option C? So we have done option B also. What about option C? In option C, you have R bar or. Okay, here again you can apply this rule: alpha implies beta equal to alpha bar or beta. So just apply this rule. Here you will get R or P. Again, this has become true. Yes or no? Again, this will become true. True or anything, that is true. True or anything is true. So finally, this is also true. Okay, so you can notice option A, that is also becoming true. Option B is also becoming true. Option C is also becoming true. So they are tautology because they are always true. They are becoming true means they are always true. Okay, let's quickly see which of these is tautology. Okay, quickly tell me. P biconditional double negation of P. So what is option A? You tell me about option A quickly. See, option A is like this: P biconditional P double bar. Okay, so what you can do? This is same as what? This is same as P biconditional P. Okay, they are same, right? Okay, notice this and this, they are same. Biconditional is true when they are same. They are same. P P. Okay, and you know that biconditional is true when they are same. So finally, this is a true. So this is definitely tautology. Yes or no? So option A is definitely a tautology. Okay, so I can say, so option A, our option A, that is option A is like this. So option A is a tautology. Okay. What about option B? That is P and P bar. That is very simple. P and P bar, that will be false. So this is contradiction. Option B is a contradiction because option B is always false. Yes or no? So option B, so contradiction. Okay. What about option C? That is tautology. Option C, that is tautology. What about option D? What about option D? Tell me. Let's check option D, that is PQ or P bar Q bar. See, option D. Option D is basically PQ or P bar Q bar. This is biconditional. Do you remember? See, look at option D. Option D is PQ or P bar Q bar. Yes or no? PQ or P bar Q bar. This is same as biconditional. Do you remember? This equation have we seen? Have you seen this equation? This is same as your biconditional. This is contingency. Yes or no? This is contingency because you can make it true, you can make it false. This is neither tautology nor contradiction. This is not a tautology. This is not a contradiction. Okay, this is at least one time true, at least one time false. So this is a contingency. Okay, so remember option D, that is a contingency. What about option E? Let me know. What about option E? That will be what? That will be tautology. Okay, option E, that will be tautology. You can check it. You can check option E. Let me check quickly. What is P implies Q implies P. So it will be very simple. It will be P implies. This will become what? Q implies P. That means Q bar or P. Okay, that will become P bar or Q bar or P. Now again you can notice here your P bar, here your P. Okay, so P or P bar, that will be true. True or anything is true. So option E, that is tautology. Is this clear? Please tell me. Okay. So very simple. So like this you can do. Can I give this question as a homework? You have to find which of the following are tautology. Two options are given to you. Option A, option B. Can I give this question as a homework? You have to find, is this tautology? Is this tautology? This is what you have to check. Okay. So take it as a homework. This is another homework. You can see. Okay. You have to find which of them is tautology, which of them is contradiction, which of them is a contingency. Okay. So this is what you have to do. Simple. Now let's move on. This is another MCQ question. You can notice this is a MCQ question. Four options are given to you. Like you can see A, B, C, D are given to you and four options. Remember, these are options. Like these are tautology, these are contradiction, and basically you have to find which option is correct. Okay, so these are options. These are not answers. These are options. Okay, so which of these options is correct? So that what you have to find out. So this is another homework. Okay, this is a MCQ question and take it as a homework. Is this clear? Please tell me. So for every homework, what you need to do, you should try the question. Okay, please try the question and put your answer in the comments with time stamp. Okay, you just put that. Okay, at this time, the answer is option A, B, C, D. Okay, which option is the answer? So pause the video, solve the question, and put your answer in the comments. Okay. Now let's see the next topic, that is converse, inverse, contrapositive. This is our next topic. What is converse? What is inverse? What is contrapositive of a conditional statement? See, converse of a conditional statement, inverse of a conditional statement, and contrapositive of a conditional statement. If you have a conditional statement, then from that conditional statement, we can create a new statement that is converse. We can create a new statement that is inverse. We can create a new statement that is contrapositive. So, if you have a conditional statement, we can create new statements, okay, which are called converse, inverse, contrapositive. Now let's see what are the definition of converse, what are the definition of inverse, and what are the definition of contrapositive. So the definition is actually very simple. If you have a conditional statement, P implies Q. If you have a conditional statement, so let's assume you have a conditional statement that is P implies Q. Okay. Now, what will be converse of this? See, this is a conditional statement. Now I can create a new statement, and that new statement will be converse of this. So what is converse of this? If I ask you what is converse of P implies Q, what that will be? Okay, what is converse of P implies Q? That will be Q implies P. So remember, converse of P implies Q, that is Q implies P. Okay, this statement you have, the converse of this statement is this statement. So I can say this Q implies P, this is converse of P implies Q. Very simple. Let's see what is inverse of P implies Q. What is inverse of P implies Q? So let's see what is that. Inverse of P implies Q, that is negation P implies negation Q. So remember, this is inverse of this statement. Okay, and similarly, what is contrapositive? How to define contrapositive of P implies Q? Let's see the definition of contrapositive. Which statement is contrapositive of P implies Q? So let me tell you, this negation Q implies negation P. This is contrapositive of P implies Q. Okay, so these are just definitions. These are very simple definitions. All you need to do, just understand the definition, remember the definition, and you can solve any question. So remember, if you have a conditional statement, then you can create new statements. You can create new statements. Okay. Now, if you have this conditional statement P implies Q, then Q implies P, that is converse. Negation P implies negation Q, that is inverse. And what is the contrapositive of P implies Q? Contrapositive of P implies Q, that is negation Q implies negation P. Okay. So remember, converse will be Q implies P. Inverse will be negation P implies negation Q. And contrapositive will be negation Q implies negation P. You have to understand and you have to remember these definitions: converse, inverse, contrapositive. Okay. Is this clear? Let me know. For example, if you have this conditional statement, then tell me, is this converse or inverse or contrapositive? What is this? Let's see this one. If this is your conditional statement, this is our conditional statement. If the weather is nice, then I will wash the car. Okay. So for this statement, this will be converse. The first one is converse. The first one is converse, right? Because you can see our conditional statement is P implies Q. Our conditional statement is if P then Q. That means P implies Q. Okay. And you can see here you have Q, here you have P. So this is converse. The first statement is converse. What about the second statement? If the weather is not nice, that means P bar. Then I will not wash my car. That is Q bar. So this second statement is inverse. So this second statement, that is a inverse. And what about the third statement? The third statement, if Q bar, then P bar, means Q bar implies P bar. Q bar implies P bar. This is contrapositive. Okay, this is a contrapositive. So very simple. The idea is very simple. For example, if this is our English, if this is our conditional statement, if P then Q, that means P implies Q. Yes or no? If P then Q, that means P implies Q. P implies Q. So converse will be what? Converse will be Q implies P. That means if I'm staying at home, then this book is interesting. If I'm staying at home, then this book is interesting. So remember, this statement is converse of this statement. What is the inverse of this statement? What is the inverse of this conditional statement? That will be, if this book is not interesting, then I am not staying at home. If this book is not interesting, then I am not staying at home. And what is contrapositive of this given statement? That will be, if I am not staying at home, then this book is not interesting. If I am not staying at home, then this book is not interesting. So very simple definitions. What are the contrapositive, converse, and inverse of this statement? Tell me quickly. Let me know. For this statement, you tell me the converse. You just tell me the converse, nothing else. You only tell me the converse. Tell me. You write the converse. Pause the video and you write the converse. The home team wins whenever it is raining. This is our conditional statement. Okay. So what will be the converse? Remember here, this is P, this is Q. So our statement is what? Can you tell me? Our original statement is what? Can you tell me our original conditional statement? What is that? Our original conditional statement, that is Q implies P. Very good. That is Q implies P. Okay, because if you remember, we have already seen this. Tell me, what is P whenever Q? Tell me what is that? Or I can say, what is A whenever B. Tell me, what is that? A whenever B. So I told you whenever is same as if. Yes or no? Whenever is same as if A if B. I can also write it if B comma A. Now this is very simple. This is B implies A. Yes or no? Okay. This we have already seen in the previous lecture. So the same thing. Our original conditional statement is Q implies P. Remember, Q implies P. So what will be converse? Converse will be P implies Q. Yes or no? So converse will be if P then Q. If P then Q. So remember, converse will be what? Converse will be if P. If home team wins. If home team wins, then it is raining. Okay, is this clear? Tell me, did you get this answer? I was asking you, what is the converse of this statement? Did you get this answer? Yes, very good. So, because remember, our given statement, understand this, that our given statement is Q implies P. If this is P, this is Q, then P whenever Q, that is Q implies P. So, the converse of Q implies P will be P implies Q. That means if P, then Q. P implies Q. That means if P, then Q. Okay. And tell me, what will be contrapositive? You tell me what will be contrapositive. What is the contrapositive of Q implies P? That will be negation P implies negation Q. Yes or no? Negation P implies negation Q. That means if negation P, then negation Q. If negation P, if home team does not win, if home team does not win, then negation Q, then not raining. Okay, this is the contrapositive. And what will be inverse? The inverse will be negation Q implies negation P. Negation Q implies negation P. That means inverse means if it is not raining, then home team does not win. That is inverse. Did you understand? Let me know. Okay. So very simple. Now let's move on. So you can see what the inverse of P implies Q. Tell me. Tell me what the inverse of P implies Q. That is negation P implies negation Q. Yes or no? What is contrapositive of P implies Q? Contrapositive of P implies Q. That is negation Q implies negation P. What is converse of P implies Q? That is Q implies P. Okay. So very simple point. You can see. Let's solve this GATE exam question. This is GATE 1998 question. What is the converse of the following assertion? I stay only if you go. We need to find out what is the converse of this statement. So first you convert this statement into propositional logic expression. Tell me what is A only if B. Tell me, when you have this type of statement, A only if B, then what is that? Let me know. A only if B. This statement, how to convert into propositional logic expression? It will be A implies B. Yes or no? We have already seen in the previous lecture that A only if B, that is same as A implies B. Okay. So here you can easily see that this statement is, what is this given statement? This given statement is basically that if I stay, then you go. Yes or no? Remember, this statement is same as if I stay. If I stay, then you go. Correct? Do you agree? This statement is same as if I stay, then you go. Because remember, A only if B, that is same as A implies B. Okay, and that means if A then B. If A then B. So A only if B, that is same as if A then B. So these two things are same. When you write A only if B, this statement is same as if A then B. Okay, very simple point. Now, so finally our statement, this is our statement. If I stay, then you go. Now what will be the converse of this statement? The converse of P implies Q, that is Q implies P, that we already know. Yes or no? So you already know that converse of P implies Q. What is that? Converse of P implies Q. that is Q implies P. Okay, so finally here I can say the converse of this statement will be, that will be, if you go then I stay. Yes or no? So the converse, finally the answer will be, our converse statement will be, our converse statement will be, that will be, if you go then I stay, because converse of P implies Q, that is Q implies P. That means if Q then P. So if you go then I stay. Okay, if you go then I stay. Okay, if you go then I stay. So tell me which option is correct. Option A is correct, yes or no? Because you can see the same thing I can say, that I stay if you go. The same thing I can say, the same thing I can say, that it is I stay if you go. Okay, if you go I stay. I stay if you go. Okay, so the answer will be option A. For this question, option A is the answer. Okay, very simple question, right? Now let's move on. So we have seen that if your P implies Q, this is your original conditional statement, then converse of P implies Q will be Q implies P. Converse of P implies Q, that is Q implies P. Contrapositive of P implies Q, that is negation Q implies negation P. Inverse of P implies Q, that is negation P implies negation Q. Okay, is this clear? Now, one important result, let me tell you. Now, one important result. So, if you have a conditional statement that is P implies Q, then tell me converse, inverse, contrapositive, which of them is equivalent to the original conditional statement? Tell me. See, if you have a conditional statement, if you have a conditional statement P implies Q, now you tell me this is the original conditional statement. The converse, inverse, or contrapositive, which of them is equivalent to this? Which of them is equivalent to this? You already know what is converse. We already know that converse will be, see, converse will be Q implies P. This will be converse. Okay. You already know the inverse. Inverse is negation P implies negation Q. Okay. And you know the contrapositive. You know the contrapositive. Contrapositive, that is negation Q implies negation P. Okay. So which of them is equivalent to the original conditional statement? You can easily create the truth table and you can check it. Okay, let me create the truth table. So you can see we have two variables. There are two propositional variable PQ. So there will be 4 rows in the truth table. There will be 4 truth value combinations: FF, FT, TF, TT. Okay. Now, what is your original conditional statement? That is P implies Q. This is our original conditional statement. Okay. What is converse? That is Q implies P. What is inverse? That is negation P implies negation Q. And what is contrapositive? Okay, so let's create the truth table of each of them. Okay, so the contrapositive, you know, that is Q bar implies P bar. Inverse, you know, that is P bar implies Q bar. Okay, and the converse, you know, that is Q implies P. Okay, that is Q implies P. So that is converse. So now you tell me the truth table of P implies Q. What is that? P implies Q. This is false only in one case. This is false when P is true, Q is false. Okay, so only in this case, P implies Q will be false. In all other cases, this is true. So this is the truth table of our original conditional statement. What is the truth table of converse? Converse is Q implies P. This Q implies P. This will be false only in one case, when Q true, P false. When Q true, P false. In this case, this converse will be false. In all other cases, converse will be true. So, can I say the original conditional statement is equivalent to converse? Can I say? Can I say they are equivalent? Can I say the conditional statement is equivalent to its converse? No, they are not equivalent. Yes or no? You can see these two, they are not equivalent. P implies Q, Q implies P, they are not equivalent. Okay, let's see the truth table of inverse. You can easily create the truth table of inverse. That will be TFTT. You can do it. You can create the truth table of contrapositive. That will be TTFT. So finally, what you got? So you got that original conditional statement is equivalent to its contrapositive. Yes or no? original conditional statement that is equivalent to its contrapositive, but that is not equivalent to converse, and that is not equivalent to inverse. So this is the result we got. What is the result? So finally I can say that, note, if you have a conditional statement P implies Q, that is equivalent to whom? That is equivalent to whom? That is equivalent to contrapositive. That is equivalent to contrapositive of itself. Yes or no? Is this clear? So very simple point that P implies Q, that is equivalent to contrapositive of itself. What is contrapositive? Contrapositive is Q bar implies P bar. Okay. And you can see they are equivalent. These two are equivalent. So every conditional statement is equivalent to its contrapositive. This is the final statement, that every conditional statement is equivalent to its contrapositive. I can say every conditional statement, any implication statement you take, that is, every conditional statement is equivalent to, or I can say basically same as, equivalent to its contrapositive. Okay, is this clear? Please tell me. So P implies Q, that is equivalent to its contrapositive. And what is contrapositive of P implies Q? That is Q bar implies P bar. So every conditional statement is equivalent to its contrapositive. Okay, but that is not equivalent to its converse. Okay, yes or no? P implies Q, that is not equivalent to its converse. P implies Q, that is not equivalent to its inverse. But P implies Q, that is equivalent to its contrapositive. So every conditional statement is equivalent to its contrapositive. Okay. Let's see the next topic, that is logic English translation. Means how to translate English statement to propositional logic and how to translate propositional logic to English. Okay. This is a very simple topic. We need to see the translation between English statement and propositional logic expression. So here, let me tell you, the most important is implication. This implication has many English translations. I told you, in propositional logic, if I write this expression, P implies Q, this is a mathematical expression, P implies Q. Okay. The English translations, there are many different English translations of P implies Q. You can see, if P then Q, P implies Q, Q if P, P is sufficient condition for Q, Q is necessary condition for P. Okay, P only if Q, you can see P only if Q. Okay, so there are many English translations of P implies Q. These we have seen in the previous lecture. In last class, we have already seen all these English translations. Okay, now let's solve this question on your screen. This question is taken from Stanford University. So you can see this question is basically based on the Jurassic Park universe. Okay. Have you seen Jurassic Park? Velociraptor in the Jurassic Park, dinosaurs. Okay. So let's solve it. You can see this statement we have, and we are representing this by propositional variable A. Okay. This statement we have represented by propositional variable B. Okay. You can see this propositional variable is representing statement I'm in my apartment right now. Okay, next, this is another statement, this is another statement. So remember, 5 propositions are given to us. We have total 5 propositions, 5 propositional variable we have. This proposition is represented by this proposition variable A. This proposition is represented by this propositional variable B. So 5 propositions and 5 propositional variables. Now let's write the expression for this statement. This English statement, how can you convert into propositional logic? What will be the propositional logic formula for this English statement? Let's see this. What this question, what this is asking, notice here. First of all, I won't be eaten by a velociraptor. What is this? Just tell me this point. I won't be eaten by a velociraptor. What is this? You can see, notice. This is E bar. Yes or no? What is E? E is saying, statement E, that is saying, I am going to be eaten by a velociraptor. So what will be this statement? Can I say this is E bar? Can I say this is Negation of E, yes or no? I won't be eaten by a velociraptor. That is negation of E. Okay. Next, there is if. There is a if. Okay. Next, what we have? There isn't a velociraptor outside my apartment. So, what is this statement? There isn't. Tell me, what is this statement? There isn't a velociraptor outside my apartment. This is same as negation of A. Yes or no? This is negation of A. Correct? Because you can see what is A. A is saying there is velociraptor outside my apartment. So this statement, there isn't a velociraptor outside my apartment, that will be A bar. So finally, what we have? Can I say we have this statement that E bar, if A bar, E bar, if A bar, E bar, you can see this is E bar, if A bar. Okay. So what I can do this? I can write it if A bar, comma E bar. And now this is your favorite. If P then Q. If P then Q, that is P implies Q. So it will be A bar implies E bar. This is your final answer. This is the final answer. Understood? Let me know. Is this clear to everyone? Simple? Okay, interesting question. So you already know P if Q, that is Q implies P. Okay, because P if Q, I can write it if Q comma P, that is same as Q implies P. Okay. Now tell me the expression for this English statement. Again, the same five propositions you have, five propositional variables you have. For this English statement, what will be propositional logic formula? What will be propositional logic expression for this English statement? Next, you can see here, there is if. Okay, we have, first of all, there is if here. So we have if. We have if. Next, what we have? Next, we have, there is a velociraptor outside my apartment, but it can't open windows. See, this is entire one statement. Do you agree with me? See, this statement, look at this statement. Can I say this is, okay, this is a statement that if there is a velociraptor outside my apartment, but it can't open windows. You know what is but? I told you but is same as and. Yes or no? But is same as and. Okay, so what we have finally, I can say that if if there is a velociraptor outside my apartment, that is A. Okay, if A but it can't open windows. It can't open windows. That means B bar. Okay, A but B bar. Okay, comma. Then what you have? Then you have, I am not going to be eaten by velociraptor. I am not going to be eaten by velociraptor. That is E bar. So E bar. So finally, this is the equation we got. Okay, now let's see how to write this. Understood? Tell me, this is what we got. We got, remember, we got this. If here we have A but B bar, comma E bar, but is same as and. So we got A B bar. If A B bar, then E bar. Okay. And that is same as if P then Q, that is P implies Q. So it will be A B bar implies E bar. This is your answer. Please tell me, did you get this? Very simple, right? Okay. So like this you can write. Remember P but Q, that is same as P and Q. Next, what is the expression for this English statement? For this English statement, what is the expression? I am only in my apartment when there is no velociraptor outside. Okay, focus. I am only in my apartment. I am only in my apartment. I am only in my apartment when there is no velociraptor outside. So, can I say that this statement is basically saying I am in my apartment only when there is no velociraptor outside? Can I say? Can I say what we are saying? We are saying that I am in my apartment only when there is no velociraptor outside. I am in my apartment. That means C. Only when there is no velociraptor outside my apartment. That is A bar. So C only when A bar. That is C only if A bar. What is only if? P only if Q. That is P implies Q. So it will be C implies A bar. So the final answer will be C implies A bar. Okay, this is our answer. Please tell me, did you understand? So these are some beautiful, cute questions. Yes or no? Remember, P only if Q. P only if Q. That is same as P implies Q. All these things we have seen in the previous lecture. So did you understand so far everything? Are you comfortable? These English to logic translation, can you do it? These were Stanford University questions. Okay, beautiful questions. Okay, now let's see. Let's solve this GATE 2014 24 question. So let's solve this GATE 2024 question. Let P and Q be following propositions. P is fail grade can be given and Q is student scores more than 50% marks. Consider the statement. Fail grade cannot be given when student scores more than 50% marks. Which one of the following is correct representation of the above statement in propositional logic? Okay, so remember two propositions are given to us P comma Q. Now, this English statement is given to us. Fail grade cannot be given when student scores more than 50% marks. The question is asking which of them is correct English propositional logic translation of this English statement. For this English statement, which of them is correct logical translation in propositional logic? Very simple. So, first of all, you tell me. Here you can see fail grade cannot be given. What is this? Remember, fail grade can be given, that is P. What is P? P is a fail grade can be given. Okay. So, fail grade cannot be given, that is P bar. This is negation of P. Then there is when. Then we have when. Then what we have? A student scores more than 50% marks. A student scores more than 50% marks, that is Q. So finally, I can say our statement is P bar when Q. P bar when Q. When is same as if. So I can say the same statement, I can say if Q comma P bar. If Q comma P bar. And that is same as Q implies P bar. So our answer will be Q implies P bar. Answer is option A. This is MCQ question. Okay. So for this question, answer will be option A. Please tell me, did you understand? Let me know. Okay, very simple question. Answer is option A. Let's solve this GATE 2017 question. Let PQR denote the statement. It is raining, it is cold, it is pleasant. Then the statement. It is not raining and it is pleasant, and it is not pleasant only if it is raining and it is cold, represented by. See, again, very simple question. First of all, you can see that PQR, these three statements are given to us. This is P. It is raining. This is P. It is cold. This is Q. It is pleasant. This is R. Okay, so three statements we have. Now the question is asking that convert this English statement into propositional logic expression. What we are saying? We are saying that it is not raining and it is pleasant. Okay, it is not raining and it is pleasant, and it is not pleasant only if it is raining and it is cold. Okay, so tell me how to write this. First of all, you tell me the red one. What will be the red one? This red one, you tell me the red one. It is raining and it is pleasant. It is raining and it is pleasant. So what that will be? You can see. Sorry, it is not raining and it is pleasant. It is not raining. That means P bar. And it is pleasant. That is R. So the red one is P bar and R. Okay, correct? The red one, because remember it is raining, that is represented by P. So it is not raining, that is P bar. So this red one, this is P bar and R. Okay. Then there is and. Then there is and, that you already know. Now what about this blue one? This blue one. It is not pleasant only if, notice this. It is not pleasant. It is not pleasant means R bar. Okay. So it is R bar only if it is raining and it is cold. That is P and Q. R bar only if P and Q. How to write this? Remember, A only if B, that is A implies B. A only if B, that is A implies B. So this is same as R bar implies P and Q. That's it. So finally our answer will be what? So remember our final answer, I'm writing it. The answer will be, that will be P bar and R. Okay, P bar and R, and because there is and here, so this and you will write here, and R bar implies PQ. R bar implies PQ. Okay, so this is the answer. So tell me which option is matching. You can see P bar and R bar implies PQ. So the answer will be option A. That's it. Very simple question. For this question, answer will be option A. This is GATE 2017 question. So please tell me, are you comfortable with English to logic translation? How to convert English statement to logic? Can you do that? Very simple. Now let's see unless keyword. This unless word in the English, how to translate this in propositional logic. In English language, have you used this word unless? So how to translate this in propositional logic? This is what we need to study. Unless word. Okay. So let me tell you, this is actually very simple. This unless, this is equivalent to if not. Very simple point. This unless you can replace with if not. That's it. Whenever you see this unless word, just replace this with if not. Okay. So when you have P unless Q, you can write it P if not Q. Now you can easily write what is P if not Q. See, P unless Q, that is same as P if not Q. That is, tell me what is that? That is if Q bar comma P, and that is Q bar implies P. Is this clear? So very simple, right? Okay. So remember, unless, that is same as if not. When you see this unless word, just remove this and write if not. Unless is same as if not. Okay. So for example, look at this statement. Jane won't go to the party unless Mary goes to the party. Okay. So that is same as what? That is same as, remember, this unless I can replace with if not. Okay. This unless I can replace with if not. So it will become if not Mary goes to party. If Mary does not go to party, then Jane won't go to party. Is this clear? Very simple. So this unless, this you can replace with if not. Simple point. Okay. You can see this unless you can replace with if not. Okay. Unless Mary goes to party, that means if not Mary goes to party, then Jane won't go to party. Okay. So unless is equivalent to if not. This is what we have seen. Now you can also see if they give you this statement, unless P comma Q. Now how to write? Very simple. Unless is same as if not. So it will be if not P, then Q. That is same as if P bar, then Q. And that is same as P bar implies Q. Yes or no? So remember, all you have to do, just replace unless with if not. Okay, that's it. So you can see here, A unless B, that is same as A if not B. Is this clear? Unless is same as if not. So A unless B, that is same as A if not B, and that is same as B bar implies A. Similarly, unless A comma B, unless is same as if not. Unless is same as if not. Okay, let me tell you one more trick. So we have seen that unless is same as if not. Whenever there is any doubt, just replace this unless with if not. Okay, let me tell you, there is another trick that is like this. See, you tell me if I have P unless Q, what this will become? P unless Q, what this will become? Let me know. Very simple. P if not Q. Yes or no? P if not Q. P if not Q. That is same as what? That is Q bar implies P. That is same as what? Alpha implies beta is alpha bar or beta. So can I say this is P or Q? Yes or no? This is same as P or Q. So did you notice that unless is basically becoming or? this unless, this is basically becoming or. That's it. Yes or no? Unless is becoming or. Okay. The same thing you can see if you have unless p comma q. Unless p comma q. Now what will happen? The same thing. Unless means if not. Okay. So it will be if p bar comma q. That is same as p bar implies q. That is same as p or q. Correct? Again, did you notice that unless is basically same as or? Unless is basically same as or. So remember, now this is the final conclusion that unless is same as or. Okay, remember unless you can replace with if not. Unless you can replace with if not, first of all, this point. And remember, unless is basically same as or. If you have A unless B, that is same as A or B. Understood? Let me know. A unless B, that is same as A or B. Okay, so these are the points. So unless is same as if not, or I can say unless is same as or. A unless B, that is same as A or B. Okay. Now let me tell you that unless is also used in conditional statements. This unless, this is also used with the conditional statement. For example, have you spoken this type of sentence in your daily life, in your real life? Have you spoken this type of sentences? If you don't leave early, you will miss the train unless train is late. Yes or no? For example, if you don't study, you will not crack the gate exam unless you are very lucky. Yes or no? Okay. So very simple point. So remember this type of statements we write, we speak in our real life. Do you agree with me? Okay. If you don't leave early, you will miss the train unless train is late. So one thing I want to ask you here, when you are speaking this complete sentence, is this one unit or is this one unit? Tell me. I'm asking, is this one unit? Is this one unit or is this one unit? Very easy. This is one unit. Agree? Yes or no? This is one unit because basically what you want to say, please see, you want to say if this, unless this. Do you agree with me? If you don't leave early, you will miss the train unless train is late. Okay. So remember, this statement is one part and this statement is another part. Do you agree? Let me know. This is very intuitive, right? Okay, this is one part. You can see this is one part. If you don't leave early, you will miss the train. This is one part. Unless train is late, that is another part. For example, if I say, if you don't study, you will not crack the gate exam unless you are lucky. So remember this unless, this is another part and this is another part. So how to translate this? Very simple. Let's see the translation. This is P, this is Q, this is R. Okay, then finally your statement, it is simply like this. Basically, if P, then Q, unless R. Okay, yes or no? Now that is same as P implies Q. Unless R, that means or R. Okay, I told you unless means or. Unless is same as or. So it will become P bar or Q or R. That's it. Is this understood? Let me know. Please tell me. Did you understand? Okay, so remember this statement. Look at this statement. If P then Q unless R. Here, do you agree? This is one part and this is another part. Do you agree that this is one part and this is another part? So very easily you can see how to translate this statement. This will be if P then Q unless R. Unless is same as or, so it will be P bar or Q or R. Okay. Now one thing I want to tell you. See, there is a coincidence. There is a coincidence. Notice this. Okay, see this. If I give you this statement, if P, then Q, unless R. Okay. Now notice what will happen. If P, then Q, unless R. Okay, let me show you one coincidence. Okay. In this type of sentence, the correct thing is that this is one part, this is another part. Okay, for example, if you don't study, you won't crack the gate exam unless you are lucky. Okay, yes or no? So this is another part, this is one part, this is the correct thing. Okay, so according to this, if we consider this one part, this is another part. If we consider this, okay, then what we are getting p bar or q or r. This is what we are getting. Now notice, by mistake, if you consider this as one part, this mistake can happen. Agree with me? Okay, by mistake, if you consider this as one part, then what we will get? Tell me. Then what we will get? Then it will be like this. P implies if a P then, if a P then. Okay, unless is or. So it will be Q or R. It will be Q or R. Then tell me, then what you are getting? Then it will become P implies Q or R. Then what you are getting? Then you are getting P bar or Q or R. So you are getting the same thing. You are getting the same thing, right? Okay. But remember, this is just a coincidence. This is just a coincidence that by mistake, if you consider this as one unit, then also you will get the same expression. But this is just a coincidence. Which one is correct? Remember, are you getting my point? You will get the same expression. This and this, they are basically same. You look at this, you look at this, they are basically same. You are getting same. Okay. So, but what is correct one? But which is the correct one? Let me know. Which is the actual correct one? Actual correct one is that you consider this as one unit and this unless is another unit. Okay. But by mistake, if you consider this as one unit, then also no problem. Then also it is not a big problem. But remember, the correct way is this is one unit, this is another unit. Okay. This is very intuitive thing. You can intuitively understand this, that this is one statement, this is entire statement. If you don't leave early, you will miss the train unless train is late. So this is just a additional part, I can say. This is just a additional part. Okay. So finally, what I want to tell you, this is what I want to tell you, that when you have this type of statement, if P, then Q, unless R. Okay. If you have this type of statement, then always remember it is same as basically this statement, if P then Q, if P then Q, unless R. Okay. And it will become P implies Q, unless that is same as or I can say unless is same as if not. Okay, unless is same as or I can say unless is same as if not. So this is what you are going to get. Okay. Now let's solve this GATE 2002 question. If X then Y unless Z is represented by which of the following formula in propositional logic? So very simple. We have already seen this. If X then Y unless Z, unless Z. Okay. So remember, the correct thing is that this is one part and this is another part. This is the correct thing. So finally, what you will get? You will get X implies Y unless is same as or. Okay. So that will be or Z. So this is our answer. Our answer, remember. Okay. So the correct answer, that is basically X bar or Y or Z. Is there any option which is matching? Any option which is matching this? No problem. Just check which option is X bar or Y or Z. Okay, let's see. So tell me, what is option A? Remember our given statement. Our given statement is if X, then Y, unless Z. Okay, this is our given statement. And for this given statement, you know the answer. The answer will be, that will be X implies Y, unless is same as or. So that is X implies Y or Z. Okay, so here we are getting X bar or Y or Z, but no option is matching. Okay, none of the option that is matching. So let's check which option is equivalent to X bar or Y or Z. Okay, so let me check. Let me check option number A. Option A is saying X and Z bar implies Y. Okay, let's simplify this. What you will get? You already know alpha implies beta. That is same as alpha bar or beta. Okay, so just apply this. So you will get x and z bar, whole bar, or y. You can apply the De Morgan law. Apply the De Morgan law, so you will get x bar or z or y. So did we get the answer? Did we get our desired answer? Yes. So the answer will be option A. You can check the remaining options also. Let's check. X and y implies z bar. Let's check option B. Option B is x and y implies z bar. So tell me, let's simplify this. What you will get? You will get x bar or y bar or z bar. So this is not correct. Yes or no? So option B is not correct. Definitely that is not correct. What about option C? Option C is saying, remember, option B is not correct. Option C is saying x implies y and z bar. Y and z bar. Let's simplify this. What you will get? You will get x bar or y z bar. Again, this is not equivalent to our given statement. So option C, that is also wrong. Okay, and what about option D? That is, let's simplify this. So tell me, if you simplify this, you will get x bar or y and z bar. Okay, you can see this is also not equivalent to our given statement. You can check it. Okay, you can check that this is also different from the given statement. So the answer will be option A. Is this clear? Please tell me. Let me know. Is this understood? This question. Very simple. Answer is option A. Okay. So we have seen how to express this implication in the English language. This is what we have seen, if you remember. Okay. So can I say what is Q unless negation P? Tell me, what is Q unless negation P? Let me know. Q unless negation P. Remember, unless, that is basically same as or. So I can say that is Q or negation P. And that is same as P implies Q. That is same as P implies Q. Or you can understand like this. Or you can understand like this, that unless is same as if not. Q if not P bar. Okay. So if not P bar, that is what? That is Q if P. That is same as P implies Q. Okay. So like this, you can understand. Is this point clear? Let me know. Very simple, right? So remember, unless is same as if not, unless is same as if not, or I can say unless is same as or. Okay. So like this. So this P implies Q. You can write it Q unless negation P. Like this also you can write. Here you can see P is sufficient condition for Q. Q is necessary condition for P. All these things we have seen in the previous lecture. Okay.